Chocolate is one of the world's most beloved creations, but each brand has its own secret recipe and process. From the clean label ingredients of Feastables to the creamy heritage of Cadbury dairy milk and the caramel-rich precision of Mars, every bar is a story of science, flavor, and craftsmanship. Today, we go inside their factories to uncover how these iconic chocolates are mixed, molded, and mastered into perfection. Feastables chocolate begins with bulk delivery of raw cacao beans. The beans arrive in large jute sacks and are poured into a vibrating hopper. The vibration sorts debris and dust from the beans. From there, a conveyor lifts the beans into a destining machine. This machine uses air jets and sieves to remove stones, metal fragments, and dense impurities. Next, the beans pass through an infrared or rotary drum roaster. The internal temperature is precisely controlled, typically between 120 degrees C and 150 degrees C. The roasting drum rotates continuously, ensuring even heat distribution. As the beans roast, moisture evaporates and flavor precursors begin to develop. The outer shells become brittle. Once roasted, the beans are fed into a winnower. This machine cracks the beans and separates the lightweight husks from the dense nibs using a combination of rollers, suction, and vibration. The result is a stream of clean, uniform cacao nibs. These nibs are conveyed to a pre-grinder. Inside, steel rollers or rotating discs crush the nibs, releasing cocoa butter and forming a thick paste called cocoa liquor. The texture shifts from gritty to smooth as the particles are reduced to below 100 microns. This liquor is held in heated tanks to maintain fluidity. A precise ratio of cocoa liquor, cocoa butter, sugar, and optional ingredients like sunflower lecithin or vanilla powder is then metered into a mixing vessel. For milk chocolate variants, milk powder is added. The mixer uses rotating paddles and scrapers to fold and blend the mixture. The dry and liquid phases integrate into a homogeneous, gritty paste. This mixture is then transferred to a refining system. Typically, it enters a 5-roll refiner. The paste moves through a series of steel rollers, each tighter than the last. The rollers spin at different speeds, shearing and compressing the particles. Particle size is reduced to 15 to 20 microns. This step gives the chocolate its smooth mouthfeel. After refining, the fine chocolate powder enters the conche. The conche is a heated trough with rotating blades. The blades knead and aerate the chocolate for hours, sometimes up to 24 hours. Frictional heat raises the temperature to 58 to 60 degrees. Acidity and volatile compounds evaporate. The texture becomes fluid and the flavor mellows. At the end of conching, the chocolate mass is pumped into holding tanks. These tanks are jacketed with hot water or oil to maintain a precise temperature and viscosity. The chocolate is now fully developed, but still needs tempering. The tempering process begins. In an automatic tempering machine, the chocolate flows through a series of heat exchangers. First, it is cooled rapidly to around 27 degrees Celsius. Then, it's gently reheated to approximately 31-32 degrees Celsius. This controlled crystallization ensures that only stable cocoa butter crystals, form 5, remain. The chocolate emerges with a glossy finish, a crisp snap, and resistance to bloom. Tempered chocolate is dispensed into polycarbonate molds using a depositor. Each mold moves along a belt under the depositor head. Pneumatic pumps release precise volumes of chocolate into each cavity. The molds then vibrate on oscillating plates to release air bubbles and level the chocolate surface. For bars with inclusions like crisped rice or quinoa, these dry ingredients are pre-weighed and dropped into the molds before or after deposition. A brief pass through a secondary vibration stage ensures even distribution. The filled molds enter a multi-zone cooling tunnel. The tunnel gradually lowers the temperature from 20 degrees Celsius to below 10 degrees Celsius over 15 to 20 minutes. Cold air circulates evenly around the molds. The chocolate solidifies and contracts, releasing cleanly from the mold walls. At the end of the cooling tunnel, a demolder inverts each mold and uses pneumatic fingers or vibration to eject the solid bars onto a conveyor. Bars with visual defects or broken corners are automatically rejected by a vision system. The flawless bars move toward the wrapping station. First, they pass under a metal detector. Any product triggering the sensor is rejected. Accepted bars proceed to flow wrapping. In the flow wrapper, film material is unwound from a large roll. Rollers and guides stretch and align the film. As the chocolate bar approaches, a photocell detects registration marks on the film. The bar is enveloped in the film and heat-sealed longitudinally along the bottom. End seals are formed using rotating crimpers that simultaneously cut and seal the package ends. Sealing jaws apply controlled heat and pressure to ensure airtight closure. Wrapped bars are transferred to a check weigher. Each bar is weighed at high speed. Overweight or underweight bars are rejected via a pneumatic pusher. Conforming bars continue on the line. Next, a robotic arm arranges the wrapped bars into a collating station. A programmable pick-and-place system grabs a fixed number of bars, usually 12 or 24, and loads them into a preformed carton or display box. The cartons are fed from a magazine and erected mechanically with glue applied by a precision nozzle. Filled cartons pass through a carton sealer. Top flaps are closed and sealed with hot melt adhesive. A roller press ensures adhesion. Barcodes and date codes are printed using an inkjet coder or laser etcher as the cartons move along. Cartons are grouped on a secondary conveyor and conveyed to a palletizing cell. Here, a robotic palletizer with suction cups or mechanical grippers stacks cartons in alternating patterns onto wooden or plastic pallets. Slip sheets may be inserted between layers to prevent shifting. Once a pallet is complete, it moves to a stretch wrapping station. A rotating arm wraps the pallet in clear stretch film from top to bottom. Tension is automatically adjusted based on load size and weight. The final wrapped pallet is conveyed to staging for outbound shipment. Throughout the process, programmable logic controllers, PLCs, synchronize timing, temperature, flow rate, and sensor feedback across the line. The entire system operates in a closed-loop, high-efficiency sequence. Raw cacao is transformed into a uniform, shelf-stable product through thermal processing, grinding, mixing, tempering, molding, wrapping, and palletizing. Each machine is tuned to maintain product consistency within tight tolerances. Distinctive mechanical features include the 5-roll refiners' progressively tighter gaps, the conch's continuous shearing and aeration, and the tempering unit's 3-zone thermal profile. These machines operate with minimal variation, ensuring texture, flavor, and finish are uniform across thousands of bars per hour. Production speeds vary by line configuration, but a high-capacity setup can process over 300 bars per minute. The synchronization between depositors, conveyors, coolers, and wrappers is maintained via servo motors and real-time monitoring systems. Cameras and load cells detect alignment, weight, and position at multiple checkpoints. Chocolate variants with mix-ins follow the same base process with additional ingredient hoppers. These hoppers dispense inclusions onto conveyor-fed molds with augers or vibratory feeders. Sensors confirm the inclusion amount by weight or volume before chocolate is deposited. For filled bars, a 2-stage depositor is used. The first depositor fills the mold cavity halfway with chocolate. The mold is vibrated and partially cooled. Then, a filling such as nut butter or caramel is injected by a piston depositor. A second chocolate layer is deposited over the filling, and the mold is vibrated again before entering the cooling tunnel. Temperature control is maintained at every stage. Heated pipes transfer chocolate between tanks and machines. Sensors constantly monitor chocolate viscosity, pump pressure, and flow rates. Any deviation triggers an automatic adjustment or line stop. All chocolate contact surfaces are made from stainless steel. CIP, clean-in-place systems, are integrated into tanks and pipes, allowing the entire system to be flushed with heated cleaning solutions and rinsed without disassembly. During production, a SCADA, supervisory control and data acquisition system, provides a real-time visual interface for operators. It displays machine status, fault alerts, production counts, and temperature trends. Cadbury Dairy Milk Chocolate begins with bulk raw materials delivered into the production facility: fresh liquid milk, granulated sugar, cocoa liquor, cocoa butter, and milk crumb. Each component is handled in temperature-controlled conditions and introduced into the system through automated silos and dosing feeders. The fresh milk is first converted into milk crumb, a defining ingredient in dairy milk's formulation. This process starts by pumping whole milk into a vacuum evaporator, where water is removed under low pressure. The concentrated milk is then combined with sugar in a heated blend tank. This mixture is transferred to rotating roller dryers. As the sweetened milk film spreads over the hot steel drums, it rapidly dries and forms a brittle, flaky layer. Scrapers detach the dried sheet, breaking it into coarse milk crumb. Milk crumb is conveyed pneumatically to storage silos, where it remains dry and ready for use in chocolate mixing. This form provides dairy milk with its unique, creamy texture and long shelf stability. Meanwhile, cocoa liquor and cocoa butter are stored separately in jacketed tanks, kept at a constant temperature to ensure flowability. The cocoa liquor, ground from roasted, winnowed cocoa nibs, is thick and rich. The cocoa butter, either pressed from liquor or sourced independently, is pale, fluid, and high in fat. Next, the primary mixing stage begins. Automated dosing systems weigh and release precise ratios of cocoa liquor, cocoa butter, milk crumb, and granulated sugar into a large horizontal mixer. This unit features dual counter-rotating shafts and side scrapers that continuously fold the ingredients. The mixture gradually develops from dry and gritty into a heavy, uniform chocolate dough. This dough is then fed into a 5-roll refiner. The refiner consists of 5 parallel steel rollers, each rotating at increasing speed. As the chocolate paste passes through each roller gap, particle size is reduced progressively, from hundreds of microns down to between 15 and 20 microns. The result is a dry, fine chocolate flake with a silky texture at the microscopic level. After refining, the chocolate flakes are transferred to the concha. The concha is a large, temperature-controlled trough equipped with heavy-duty rotor blades. The chocolate is kneaded continuously with friction-generating heat. Temperatures rise to around 55 degrees Celsius. This process can last from several hours to over a day, depending on the desired flavor development. Volatile acids are driven off, moisture is reduced, and cocoa solids are fully coated with fat, creating a smooth, aromatic chocolate base. Following conching, the chocolate mass is pumped through heated pipes into intermediate holding tanks. These tanks maintain the chocolate at a constant temperature to preserve its fluidity and prevent premature crystallization. Agitators inside the tanks ensure uniform consistency and prevent settling. From here, the chocolate undergoes tempering. An automatic tempering machine circulates the chocolate through a sequence of heat exchangers. First, the temperature is raised to fully melt all cocoa butter crystals. Then, the chocolate is cooled to about 27 degrees, prompting the formation of stable seed crystals, form phi. Finally, it is reheated slightly to around 31-32 degrees Celsius, dissolving unstable crystals, but preserving the desirable structure. This gives the final chocolate its signature gloss, snap, and resistance to fat bloom. Tempered chocolate flows into a depositor system. Polycarbonate molds pass beneath the depositor head on a continuous belt. precision nozzles fill each mold cavity with a set volume of liquid chocolate. For filled variants, a stage depositor is used. A bottom chocolate layer is poured and cooled, followed by a filling injection, such as caramel or nougat, and topped with another chocolate layer. Molds then travel onto vibrating platforms, which shake out air bubbles and level the surface. The vibrating phase lasts just a few seconds, but is crucial for creating a smooth finish and ensuring complete mold fill. Next, the filled molds enter a multi-stage cooling tunnel. This enclosed chamber has progressive cooling zones, starting around 20 degrees Celsius and decreasing to below 10 degrees Celsius. The controlled descent in temperature allows the chocolate to solidify evenly and contract slightly, easing release from the molds. Cold air is recirculated uniformly to maintain consistent crystallization. At the tunnel's exit, a demolding station uses a combination of mechanical inversion and pneumatic taps to dislodge the solidified bars from the molds. These bars land precisely onto a moving conveyor. An integrated vision system scans each piece for defects, such as incomplete fill, surface marks, or cracks. Imperfect bars are diverted via an automated rejector gate. Perfect bars continue toward packaging. First, they pass through a metal detector which scans for ferrous and non-ferrous particles. Cleared bars enter the flow wrapping system. In the flow wrapper, a printed foil wrapper is unwound from a roll and cut to size. As the chocolate bar moves along the conveyor, it is enveloped in the wrapper. A heated crimp sealing mechanism closes the back seam and simultaneously cuts and seals both ends. The wrapping film is heat sensitive and printed with registration marks to align branding and ensure uniform presentation. Wrapped bars move along a conveyor to the check weigher. Each package is weighed at high speed using load cells. Any bar outside the preset weight tolerance is immediately rejected. Compliant bars continue to cartoning. Here, an automated carton erector forms cardboard display boxes. A robotic pick-and-place arm loads wrapped bars into the cartons, arranging them in fixed rows. Hot melt glue is applied to close the carton flaps, and a compression roller seals them firmly. Cartons are then printed with best before dates and batch codes using a high-speed inkjet printer. A final vision check confirms the code, legibility, and positioning. Grouped cartons proceed to palletizing. A robotic system picks up multiple cartons at once using vacuum grippers or mechanical arms. It stacks them onto standard pallets in a predetermined configuration, alternating layers for stability. In some cases, slip sheets are added between layers. Completed pallets advance to the stretch wrapping station. A rotating arm encircles each pallet, applying pre-stretched film under controlled tension. This secures the load for storage or transport without crushing the cartons. Throughout the entire Cadbury dairy milk production process, every system is managed by a centralized PLC, programmable logic controller, network. These systems coordinate flow rates, temperature set points, and equipment timing. Sensors along each conveyor track product speed, mold position, and fill levels in real time. Data from all units feed into a SCADA, supervisory control, and data acquisition interface, allowing operators to monitor trends, alarms, and equipment health at a glance. Flow meters, load cells, thermocouples, and vision sensors ensure that the chocolate's physical and visual properties are maintained to exact standards. In multivariant production lines, switchovers between bar sizes or recipes are handled via modular machine components. Depositor heads, mold formats, and wrapping film rolls can be exchanged with minimal downtime. Servo motors and memory-driven positioning systems recalibrate machinery for different dimensions automatically. For filled bars or multi-layer variants, rotary depositors inject fillings such as fudge, caramel, or fruit puree between chocolate layers. These fillings are stored in separate heated tanks and dispensed through jacketed pipes to maintain flow without separation. Every chocolate contact surface is stainless steel, designed for CIP, clean-in-place systems. After production cycles, cleaning valves open and circulate alkaline detergents, followed by a water rinse to sanitize the interior of tanks, pipes, and mixers. The entire Cadbury dairy milk process, from fresh milk to molded bar, operates in a closed, highly automated loop. Thermal stages, particle size reduction, emulsification, crystallization, and molding are orchestrated to maintain the exact texture, sweetness, and melt profile that define the finished product. From the rolling dryers that turn milk into crumb, to the 5-roll refiners that shear cocoa particles, to the vibrating mold beds and precision wrapping crimpers, each machine plays a role in transforming bulk ingredients into a consistent, shelf-ready chocolate bar. High-capacity lines can produce thousands of bars per hour, with conveyors spanning hundreds of meters across multiple zones. The process flow is linear, but segmented into temperature, flow, and pressure-controlled modules, each ensuring precise control over the material's transformation from liquid to solid, from raw to refined. Mars chocolate bars begin with the precise handling of their core components: sugar, cocoa mass, cocoa butter, skimmed milk powder, glucose syrup, lactose, and vegetable fats. Each ingredient is delivered in bulk. Liquids stored in jacketed stainless steel tanks, powders and solids transferred through enclosed pneumatic conveyors into weight-controlled silos. The process initiates with the creation of the chocolate base. Cocoa liquor, also known as cocoa mass, is pumped from heated storage tanks into a large jacketed mixer. Along with it, metered quantities of cocoa butter, sugar, and milk powders are added. This mixture is stirred with high-torque paddles under heat to form a semi-dry paste. The mixing cycle is tightly controlled to ensure homogeneity of particle distribution before size reduction. The paste moves next into a 5-roll refiner. This machine consists of 5 steel rollers aligned horizontally, each rotating at progressively higher speeds. The chocolate mass is compressed and spread across each roller in sequence. As it passes through the narrowing gaps, particle size is reduced to between 15 to 20 microns, creating a fine, uniform flake that feels smooth on the tongue. These flakes are transferred to conchas, elongated troughs equipped with rotating agitators. The friction between the rotating arms and the flakes generates heat, bringing the chocolate to around 55 degrees. This step is vital for flavor development and smooth texture. During conching, volatile acids and moisture evaporate, and cocoa solids are thoroughly coated with fat. The result is a free-flowing, aromatic chocolate liquid. Tempered storage tanks receive the conched chocolate. These tanks are equipped with agitation blades and heat exchangers, maintaining a stable temperature to keep the chocolate fluid. From here, it is pumped into tempering units, where it undergoes controlled cooling and reheating. The goal is to crystallize only the stable Form V cocoa butter crystals. Tempering involves 3 precise temperature stages. First heating the chocolate to about 45 degrees Celsius, then cooling it to 27 degrees Celsius to initiate crystal formation, and finally reheating to around 31 degrees Celsius. This thermal profile ensures the finished chocolate has a shiny appearance, a sharp snap, and resistance to blooming during storage. While the chocolate is being prepared, the nougat base is made separately. A pre-blend of sugar, glucose syrup, egg white powder, milk powder, and salt is mixed in a high-speed planetary mixer. The mixture is heated to a specific temperature, typically around 120 degrees Celsius, and whipped under pressure. As air is incorporated, the texture becomes light and spongy. The output is a warm, aerated nougat mass, which is discharged onto a belt in a continuous sheet. This nougat sheet moves through a calibrating roller system that flattens it to the target thickness, typically 12 to 16 millimeters. The sheet passes under an infrared scanner to check its uniformity. Next, it enters a chilling tunnel, where cold air reduces the temperature to stabilize its structure for the next layer. Once chilled, the nougat layer receives a caramel topping. Caramel is prepared in a separate, continuous cooker. A mixture of glucose syrup, sweetened condensed milk, and vegetable fat is cooked under vacuum to around 118 degrees. It is then cooled slightly and deposited onto the nougat sheet through a wide slot applicator. The caramel spreads across the surface in a uniform layer, with its viscosity controlled by temperature. The combined nougat caramel sheet passes through another set of rollers to achieve precise height. It then enters a second cooling tunnel, where the caramel layer is stabilized and slightly hardened. After cooling, the multi-layer slab is cut into individual bar-sized fingers using a guillotine cutter. First, the slab is cut laterally into long ribbons. Then, rotary knives or ultrasonic blades slice each ribbon perpendicularly into pieces of exact length. The blades operate at high speed, synchronized with the belt to avoid distortion or smearing. These cut fingers are spaced evenly and conveyed toward the enrobing station. Enrobing is the process where each bar is fully coated in liquid tempered chocolate. The enrober has a curtain of flowing chocolate that falls from a weir. As the bars pass beneath the curtain, chocolate coats the top and sides. A bottoming station simultaneously floods the base with chocolate. Excess chocolate is removed by an air knife that blows a controlled jet of air, creating the classic ridge surface on top of the bar. Enrobed bars immediately enter a cooling tunnel. This tunnel consists of several cooling zones, gradually reducing the temperature from ambient to around 8 to 10 degrees Celsius over 5 to 7 minutes. Chilled air circulates from multiple directions to ensure even setting of the chocolate coating. Exiting the cooling tunnel, the now solid Mars bars pass through a metal detector for contamination control. Each bar is scanned for ferrous and non-ferrous metal fragments. Bars that pass inspection proceed directly to wrapping. The wrapping system is a high-speed flow wrapper. Printed film is unwound and cut to size by a rotary knife. As each bar approaches, the film is formed around it and sealed lengthwise along the bottom with a heat bar. Crimpers then seal both ends and cut between each unit, forming an airtight package. The position of the branding and barcode on each wrapper is controlled by registration marks and optical sensors. Each wrapped bar moves to a check weigher that confirms product weight. Bars falling outside the set, tolerants are rejected via a pneumatic arm. Acceptable bars move onward to collation and cartoning. A collating conveyor arranges the bars into rows and stacks them in groups. Robotic pick-and-place arms, equipped with vacuum heads, lift the grouped bars and insert them into pre-formed cartons. The cartons are formed from flat blanks by a mechanical erector, which folds and seals the base flaps with hot melt glue. Filled cartons pass through a closure unit where top flaps are folded and glued shut. The cartons then pass under an inkjet or laser coder, which prints best before dates, production times, and batch codes on each unit. For bulk distribution, cartons are transferred to an automated palletizer. A robotic arm places the cartons in pre-programmed patterns on a standard pallet. Slip sheets are inserted between layers as needed. Once the pallet is complete, it is stretch wrapped by a rotating arm that applies plastic film from top to bottom under tension. Each segment of the Mars bar production line is governed by PLCs, programmable logic controllers, which synchronize all motor functions, flow rates, temperatures, and timing sequences. Sensors placed throughout the system continuously feed data to a SCADA, supervisory control, and data acquisition interface. Operators monitor real-time performance, trend data, and alarms from centralized control panels. Temperature sensors in the caramel cooker, nougat mixer, and chocolate tempera maintain thermal precision within plus a 0.5 degree Celsius. Load cells in dosing hoppers regulate ingredient input by mass. Viscosity sensors in chocolate tanks and caramel pipelines provide feedback to flow controllers and ensure consistency during deposition. Mars bar production lines are modular and capable of format changes. Swappable depositor heads, adjustable belt guides, and programmable cutter settings allow the system to handle different bar sizes, weights, or recipe variants. The enrobing line can switch chocolate types, milk, dark, or white, by flushing the system with CIP, clean in place, protocols. CIP systems are built into tanks, pipes, and enrobers. These automated cleaning cycles use heated caustic solutions followed by sterile water rinses. The process is run between product types or during shift changes. Filled bar variants, such as those with peanut butter, cookie dough, or layered textures, use dual-stage deposition. After the nougat base is laid down, a second depositor applies a defined filling stripe. A heated spreader may be used to smooth viscous fillings. The caramel and chocolate enrobing proceed normally after this stage. Production lines for Mars bars typically operate at speeds up to 300 bars per minute, depending on bar size and configuration. The entire process, from raw ingredients to palletized cartons, takes place over a footprint of several hundred meters of continuous machinery, arranged in a linear but interlinked layout. Distinctive mechanical features include the dual cooling tunnels for nougat and caramel stabilization, the high-pressure air knife for chocolate surface texturing, and the inline ultrasonic blade system that cuts without deformation. Every component in the process is engineered for consistency. Chocolate viscosity is regulated through controlled fat content and shear mixing. Caramel texture is tuned by managing cooking time and water activity. Nougat aeration is monitored with pressure transducers and density meters in real time. The Mars chocolate bar emerges from this high-precision mechanical sequence as a fully formed, enrobed, wrapped, and coated product, engineered for consistency in texture, layering, and appearance. Every detail, from the shear of the 5-roll refiner to the calibration of caramel applicators, contributes to the uniformity of each bar produced. The process begins with the reception of raw cacao beans. These arrive in large burlap sacks, which are automatically tipped into a stainless steel hopper. The hopper feeds a vibratory conveyor, shaking the beans in a controlled rhythm to remove debris and small stones. As the beans travel, high-powered magnets and air jets eliminate metallic fragments and lighter contaminants. Once cleaned, the beans move into the roasting chamber. This is a horizontal, drum-style roaster with precise temperature zones along its length. The beans are roasted between 120 degrees Celsius and 150 degrees Celsius for 30 to 45 minutes, depending on origin and moisture content. Inside the rotating drum, baffles lift and drop the beans repeatedly to ensure even exposure to heat. The surface crackles as volatile acids are driven off, and the aroma intensifies. Roasting profiles are strictly controlled using infrared sensors and thermal probes. After roasting, the beans exit into a rapid cooling system, a double-jacketed air cooling tunnel that quickly brings the temperature down to prevent over-roasting. As the beans cool, they're conveyed to the winnowing station. Here, a precision cracking roller gently fractures the outer shells. The mixture then passes through an ascending air column. Shells, being lighter, are blown upward and extracted into a cyclone separator. The heavier nibs fall downward, separated cleanly. The nibs are then routed into the liquor grinding system. This involves a two-stage reduction process. First, a coarse grinder reduces the nibs into a paste-like mass using granite rollers. This mass, still gritty, feeds into a 5-roll refiner. The rolls are made from hardened steel and arranged in descending gap widths. The rollers spin at increasing speeds to shear the particles down to 20 microns. During this stage, the paste becomes smooth and glossy, now known as chocolate liquor. From the refiner, the liquor is pumped into a conching machine. This is a long, horizontal tank with heavy granite paddles. The paddles rotate slowly but forcefully, kneading the liquor for up to 72 hours. During this process, frictional heat raises the temperature to 50-60 degrees Celsius. This drives off unwanted volatiles and enhances texture. As it churns, the chocolate undergoes subtle flavor transformation and becomes fluid, velvety, and aerated. At this stage, additional ingredients are introduced through precision feeders. Sugar is added via a sealed screw conveyor that meters crystalline particles in carefully measured doses. Milk powder, if producing milk chocolate, is pre-blended with a small portion of cocoa butter before being added. The mix is tested repeatedly with inline viscometers and particle size analyzers to ensure consistency. Next, the chocolate moves into the tempering system. This consists of 3 stainless steel heat exchangers that rapidly cycle the chocolate through defined temperature curves. The liquid chocolate is cooled from 45 degrees Celsius down to around 27 degrees Celsius and then reheated to 31 or 32 degrees Celsius. This carefully controlled crystallization process encourages the formation of stable cocoa butter crystals, Form 5, which gives the final chocolate a glossy finish and crisp snap. Once tempered, the chocolate is ready for molding. It flows into automated depositor heads mounted above polycarbonate molds. Each head features multiple precision nozzles controlled by servo motors. The nozzles deposit exact volumes of chocolate into the cavities, synchronized with the moving mold belt below. Vibration tables mounted beneath the molds shake rapidly, eliminating trapped air and evening out the surface. The molds enter a cooling tunnel, a refrigerated corridor where temperature and humidity are tightly regulated. Inside, a chilled airflow passes over the molds for 10 to 15 minutes, bringing the chocolate down to 8-10 degrees Celsius. This solidifies the product and locks in the tempered structure. Once cooled, the molds are inverted and gently flexed by mechanical arms to release the solid chocolates. They drop onto a food-grade conveyor belt, which directs them to the decorating and enrobing section. Here, high-speed cameras inspect the chocolates for surface defects, rejecting any that are misformed or marred. If filled or layered chocolates are being produced, the process diverges earlier. In that variation, the molds receive only a thin chocolate shell in the first deposit. These shells are then cooled, filled with praline, ganache, or fruit paste through precision piston fillers, and then sealed with a final layer of tempered chocolate before full cooling. Back on the main line, the finished solid chocolates enter the enrobing tunnel if they require coatings. This consists of a continuously flowing curtain of tempered chocolate falling from a weir system. The chocolates pass beneath the curtain on a wire mesh belt, receiving a uniform coating. Excess chocolate is blown off the bottom by air knives positioned beneath the belt. After enrobing, the products move through another cooling tunnel. This secondary tunnel is slightly longer and maintains cooler airflow at 6-8 degrees Celsius to ensure the coating sets with a uniform sheen. Inside, multiple temperature zones gradually reduce the product temperature to avoid bloom or condensation. Next is the decorating phase. This station uses robotic arms fitted with ultra-fine nozzles and stampers. The arms are guided by a 3D vision system to identify the orientation of each piece. Depending on the product, they may apply fine chocolate stripes, edible gold dust, cocoa powder, or even embossed logos using heat press stamping heads. Some lines include a nut topping mechanism that drops single pistachios or almonds onto the still soft chocolate surface with pneumatic precision. From here, the chocolates move to the buffering conveyor. This is a serpentine belt that temporarily holds products in case downstream machines slow down or halt. It prevents product collisions and maintains production flow without pause. Once flow resumes, the chocolates proceed to the wrapping line. The wrapping process begins with a high-speed feeder system. Chocolates arrive in single file along a narrow conveyor aligned by adjustable guide rails. As they approach the wrapping unit, an optical sensor scans each piece to verify orientation and spacing. A star wheel indexing system captures each chocolate in a rotating pocket, ensuring it enters the wrapping machine at precisely timed intervals. For individually wrapped pieces, the wrapping style depends on the product type, either fold wrap, twist wrap, or flow wrap. Fold wrap is used for rectangular or square chocolates. A continuous roll of foil, ends, often metallized polypropylene or laminated aluminum, feeds into a cutting station. A servo-driven knife slices the foil into perfectly sized sheets. A vacuum picker transfers each sheet onto a wrapping plate where a chocolate rests. Pneumatic folders quickly tuck each edge of the foil around the chocolate with clean, creased folds. And heated plates press the final seam to ensure adhesion without adhesives. In twist wrapping, used for rounded or pillow-shaped pieces, the chocolates are dropped into film pockets on a rotating turret. As they spin, two heated jaws grip the ends of the film and twist them in opposite directions in a single, fluid motion. The result is a tight double twist at both ends with no glue, secured purely by friction and film memory. Flow wrapping is reserved for bars or longer chocolates. Chocolates move onto a horizontal flow wrapper in perfect rows. A forming box folds a continuous film web into a U-shape around the moving product stream. Longitudinal sealing wheels fuse the film along the bottom seam using heat and pressure. Rotary end sealers then crimp and cut between each chocolate in one continuous motion. The result? A tight, seamless pillow pack with serrated edges. Once wrapped, products pass under a metal detector integrated with an automatic reject arm. Any contamination triggers an immediate air jet that diverts the product off the main line without interrupting flow. Approved chocolates continue to the labeling and grouping section. For chocolates requiring labels or tamper-evident seals, a label applicator aligns pressure-sensitive labels onto the wrapper surface with micron-level accuracy. For sealed tags or holograms, a rotary arm applies the label with static discharge to eliminate air pockets. High-speed vision systems verify placement and orientation, rejecting any misaligned units. Next, the wrapped chocolates are grouped into sets for final boxing. This is handled by a Delta robot pick-and-place system. Using 3 arms mounted on a gantry and guided by overhead cameras, the robots lift chocolates from the conveyor and deposit them into plastic or cardboard trays. The trays are held on index pallets that move step by step beneath the robot's reach. Depending on the SKU, arrangements may be linear rows, nested pyramids, or offset diagonals. If the product is a boxed chocolate assortment, the process diverges again. Assorted trays begin with an injection molded plastic insert, which is automatically placed into a folding carton. Chocolates are sorted by type and delivered to multi-head pickers. Each picker arm uses vacuum suction or soft rubber grippers to lift specific chocolates and place them in precise tray compartments. The sequence is synchronized to ensure correct assortment patterns. No duplicates, no gaps. Once loaded, these trays move to the lid application station. A folding carton blank is fed into a forming mandrel where pneumatic fingers erect and glue the box around the insert. A transparent film or foil seal is sometimes heat applied across the top, shrinking snugly into place. Then, a decorative lid is pressed on with a spring-loaded arm to achieve a flush seal. If a rigid luxury box is used, an entirely separate line assembles it. Die-cut cardboard is laminated with printed paper and hot-pressed into box forms. Magnets or ribbon closures are inserted automatically by articulated tools. The finished boxes are then transferred via robotic arm to receive their filled trays. From here, final boxing and case packing begins. Chocolates, now individually wrapped or boxed, arrive on a wide accumulation belt. Automatic collators organize them into bundles of 6, 12, or more, depending on shipping unit configuration. These bundles are pushed into carton erectors where flat corrugated blanks are folded around them, glued and pressed shut. Some lines use wraparound case packers. In this method, the grouped products are held stationary as a blank corrugated sheet is wrapped around all sides. Mechanical arms fold the flaps, apply hot melt glue, and compress the bundle into a sealed shipping case. These cases exit onto a short conveyor where industrial inkjet printers mark each side with batch numbers, timestamps, and QR trace codes. The case is then moved to the palletizing zone. Here, a robotic arm with a vacuum plate or gripper head arranges cases onto pallets. Each layer follows a programmed stacking pattern, alternating orientations for stability. After each layer, a slip sheet may be inserted by an automated feeder. Once the full stack is complete, often up to 2 meters high, the pallet is conveyed to a stretch wrapping machine. The stretch wrapper features a rotating turntable and a film carriage that moves vertically. As the table spins, the carriage stretches and applies multiple layers of plastic film under tension. This secures the load tightly and protects against moisture and dust. Some systems include a top sheet applicator that lays a waterproof plastic sheet across the top before wrapping. Finally, the fully wrapped pallets are conveyed through a weight check station and scanned by a vision system for final verification. They are now ready for shipment. A precisely manufactured, delicately handled series of chocolates transformed through over 24 distinct mechanical stages from raw bean to boxed luxury. For filled and layered chocolates, the factory employs a specialized multi-stage molding line. This system operates on a closed-loop conveyor that continuously cycles polycarbonate molds through a sequence of precisely timed stations. Each mold contains multiple cavities, and every station in the circuit performs a distinct action in the assembly of complex, filled products. The process begins with the shell forming station. A depositor head releases a measured volume of tempered chocolate into each mold cavity. Immediately, the molds move to a tilting station, where they are flipped and vibrated simultaneously. Centrifugal force causes the chocolate to coat the sides and bottom of each cavity evenly, leaving a hollow center. Any excess chocolate flows out and is reclaimed. After inversion, the molds pass under a chilled airflow, rapidly setting the shell. Once the shell is solidified, the molds continue to the filling station. This unit features servo-controlled piston depositors mounted above each cavity. The fillings are stored in heated hoppers to maintain fluid consistency. These can include hazelnut praline, fruit compotes, flavored ganache, caramel, or nut pastes, each delivered through dedicated nozzles. The depositors lower and inject precise quantities into each chocolate shell without disturbing the walls. Viscosity is controlled via inline heating coils wrapped around the filler lines. Every filling passes through mass flow meters to ensure consistency across thousands of units. Between each product type, CIP, clean-in-place systems, purge the lines with high-pressure heated water, followed by compressed air to eliminate cross-contamination. Next, the filled molds pass through a brief cooling tunnel. This lowers the filling temperature just enough to create a thin surface skin, ensuring it doesn't mix with the final chocolate seal. At the cap sealing station, another depositor head applies a top layer of tempered chocolate, sealing each cavity shut. This chocolate is deposited with high precision, covering the filling completely and fusing to the shell edges. Vibration tables beneath the molds remove trapped air and ensure a flush finish. The molds then enter a long cooling tunnel, typically spanning over 10 meters. This tunnel contains multiple chilled zones that gradually reduce product temperature from 30 degrees Celsius to under 10 degrees Celsius. The slow, staged cooling prevents shrinkage or cracking and allows the chocolate to fully contract away from the mold walls. Once cooled, the chocolates are ejected mechanically. Pneumatic plungers behind each mold cavity gently push the finished pieces downward onto a soft conveyor. These filled chocolates proceed to surface treatment. For layered chocolates, a similar system is used with key variations. After the first shell is deposited and cooled, a layer of inclusions, such as crushed nuts, cookie pieces, or fruit granules, is sprinkled into the mold by an oscillating vibratory feeder. A light pressure roller presses the inclusions into place. Then, a layer of filling is added, followed by a capping layer of chocolate. This creates a tri-layered cross-section when cut or bitten. Aerated chocolates follow a different method entirely. Here, the chocolate is first fed into a pressurized vacuum chamber. Under controlled vacuum, nitrogen gas is injected into the chocolate stream through a sparger, a perforated titanium rod. The gas forms microbubbles, which are then locked in by suddenly returning the chamber to atmospheric pressure. The now aerated chocolate has a mousse-like texture, yet remains stable once cooled. This aerated mixture is deposited into molds using modified volumetric heads that prevent bubble collapse. Because of the internal gas structure, aerated chocolates are cooled more gently to avoid rapid contraction. They pass through a specialized tunnel with fine-tuned temperature gradients that stabilize the internal structure. Some advanced variations include dual flavor split molds. These use two separate depositors operating in tandem, each filling half of the mold cavity with a different chocolate, such as milk and white or dark and ruby. A precision divider plate inside the nozzle ensures a clean, vertical split. The chocolates are deposited simultaneously, then vibrated and cooled, just like single origin types. Another variant involves inclusions in the chocolate itself. Before deposition, the base chocolate is mixed with particulate ingredients in a jacketed mixing bowl. These include puffed rice, freeze-dried fruit bits, chopped nuts, or biscuit crumbs. Agitators inside the bowl maintain even suspension. A positive displacement pump pushes the mixture through a large bore pipe to prevent clogging. Depositor heads with wider nozzles are used to handle the textured mass. For decorative layering, some lines use transfer film technology. A thin acetate film, printed with edible cocoa butter designs, is cut into sheets and placed on the bottom of each mold before chocolate is deposited. When the chocolate sets, the design transfers from the film onto the chocolate surface, creating intricate visual patterns. After cooling, the film is peeled away, leaving behind a vivid imprint. In other cases, chocolate pieces are stamped with embossed patterns or logos. After demolding, the chocolates move under a stamping head fitted with a heated metal die. The die is pressed lightly onto each piece, embossing it with a brand mark, pattern, or crest. The metal stamp is kept at 32 degrees Celsius, just warm enough to soften the surface without damaging structure. At this point, finished chocolates, whether filled, layered, aerated, or decorated, are directed toward the enrobing and topping station, if required. Some filled pieces receive an extra chocolate shell by passing through the enrobing curtain. Toppings such as sea salt flakes, crushed pistachios, or cocoa nibs are dispensed through multi-channel feeders synchronized with the belt speed. Each topping module includes a vibration sieve that controls granule size and drop rate. Sensors monitor belt occupancy to ensure no topping lands between products, minimizing waste. A gentle pressing roller may follow to embed toppings into the soft coating before cooling. Some premium chocolates are dusted with edible luster dusts or shimmer coatings. These powders are dispensed in an ultra-fine mist using electrostatic sprayers. The particles are positively charged as they exit the nozzle, adhering uniformly to the negatively charged chocolate surfaces. This creates a metallic or pearlescent finish with minimal overspray. For chocolates that require a hard shell glaze, a final step involves a rotating drum polisher. Chocolates are fed into the drum, which tumbles them gently while applying a thin mist of food-grade shellac or gum arabic. Internal warm air jets dry the glaze instantly, leaving a glossy, protective surface. Before reaching packaging, all finished chocolates pass through a multi-stage inspection tunnel. This includes laser-based shape detection, surface color analysis, and infrared temperature scanning. Products outside tolerance limits are ejected into designated bins. The final stage begins at the primary packaging line, where individual chocolates are grouped, positioned, and inserted into final, retail-ready formats. This step varies depending on the packaging style: rigid boxes, folding cartons, sleeve wraps, trays, tins, or multi-compartment assortments. Each format requires a dedicated configuration of pick-and-place systems, folder gluers, and sealing units. For rigid box assortments, chocolates arrive on an indexed belt and are picked by high-speed Delta robots equipped with vacuum suction heads. These robots place the chocolates into thermoformed plastic inserts, which are held stationary within open-bottomed rigid boxes. The inserts have precisely molded cavities matched to the contour of each chocolate piece. The robot arms adjust their speed and angle using dynamic feedback from overhead 3D scanners to avoid any misalignment. Once all cavities are filled, the boxes proceed to a film sealing station. Here, A roll of transparent BOP film is unwound, cut into sheets, and laid across the surface of the tray. A heated sealing plate presses the film into place, fusing it along the box edges to create a tamper-evident, airtight seal. The temperature of the sealing head is closely monitored by embedded thermocouples to maintain optimal adhesion without distorting the tray. For folding cartons, a different approach is used. Flat carton blanks, pre-printed and die-cut, are fed from a magazine stack into a carton erector. Mechanical arms fold the blank along pre-scored lines and apply hot melt glue in strategic points using precision nozzles. The forming mandrel compresses the carton into shape as it moves along the conveyor. Simultaneously, chocolates are grouped upstream by a collator belt, which aligns them into patterns matching the carton's internal layout. A pneumatic pusher slides each group into the open cartons as they move past. Once filled, the top flaps are folded and glued shut in a continuous motion. Some cartons are sealed with ultrasonic bonding, especially when glue-free closures are preferred. Specialty packaging formats, like sleeve-wrap trays, begin with a plastic or cardboard tray filled with chocolates using robotic placers. A printed sleeve, flat and folded, is then placed over the tray. A servo-controlled banding unit wraps the sleeve snugly and applies a heat pulse to seal the overlap. These sleeves often include die-cut windows or embossing, requiring precise alignment during application. For metal tins or embossed boxes, an overhead conveyor delivers empty tins into position beneath the filling heads. Chocolates are stacked by robotic arms, using multi-head grippers that rotate to fit varied geometries. Once filled, the tins are lidded by a lid placement mechanism equipped with pneumatic actuators. The lid is pressed into place with a calibrated force to ensure a snug fit without warping the metal structure. In premium lines, inserts and accessories are added next. These include product guides, tasting menus, or promotional leaflets. A sheet feeder places the inserts into each box before final closure. In some configurations, a robotic arm adds a protective paper layer or a foil cover between the chocolates and the lid. When ribbon closures are required, a secondary robot wraps and ties the ribbons automatically using twin spindle tensioners and soft grippers. After primary packaging, products move into the overwrapping unit, especially for premium and seasonal items. A continuous film roll feeds through a forming collar to enclose each box. A fin sealer applies pressure and heat along the bottom seam, while side sealers tuck and seal the ends into neat folds. A cooling plate downstream sets the film structure immediately after sealing. Optional tear strips or easy open tabs are applied at this stage. These are pre-cut film sections with embedded threads or adhesives that allow consumers to open the product without tools. A precision applicator adds them just before the film is sealed, embedding them into the plastic without disturbing box integrity. Next is batch labeling and coding. An inkjet printer or laser etcher marks each box with its batch number, manufacturing date, expiration date, and unique identifier. For export products, a vision verification system checks every printed code in real time and compares it against the product database. Any mismatch causes an automatic ejection by a pneumatic diverter. Then, boxes enter the case packing line. A robotic case packer arranges the boxed units into shipping cartons according to a pre-programmed pattern. Each case is assembled from flat blanks in an automatic erector. Once filled, the case is sealed using a high-speed tape applicator or hot melt glue system. The type of seal depends on the distribution channel and climate conditions expected during transit. Some boxes are stacked vertically, while others lie flat, depending on product fragility and presentation. If protective dunnage or air cushions are required, an integrated dispenser adds these into the case before sealing. Completed cases are printed with destination codes and passed through a check weigher, which confirms that each box is within expected weight tolerances. At the end of the line, full cases are transferred to the palletizing system. A robotic palletizer uses a vacuum plate or mechanical gripper to stack the cases onto pallets in a staggered pattern. The stacking sequence is designed for maximum load stability. Between layers, corrugated slip sheets are automatically inserted from a magazine. Once the pallet reaches the target height, typically 1.8 to 2 meters, it is conveyed to a stretch wrapping machine. The turntable rotates the pallet while a film carriage moves vertically, wrapping it in multiple layers of stretch film. Tension sensors ensure that the film applies consistent pressure without crushing the product. For export pallets, a top sheet dispenser adds a final moisture barrier before wrapping is completed. The final wrapped pallet moves to the finished goods staging area. Here, each pallet passes through a scanning tunnel that records its dimensions, weight, and barcode data into the warehouse management system. Automated guided vehicles, AGVs, retrieve the pallets and deliver them to temperature-controlled storage areas where ambient humidity and temperature are monitored continuously. In some specialized lines, climate conditioning is introduced post-packaging. Products enter a controlled chamber that simulates various storage conditions. For instance, rapid temperature cycling from 10 degrees Celsius to 30 degrees Celsius to ensure product stability. Chocolates are held in this chamber for several hours before release to shipping to verify that they maintain integrity under stress. Before release, a final quality sampling system selects random units from each production batch. These samples are conveyed to a physical and sensory testing station, where robotic arms manipulate the products through breakage resistance tests, surface gloss readings via reflectometers, and cross-sectional scanning via laser slicers. The internal structure is analyzed for air pockets, alignment of layers, and crystallization consistency. The process begins with the sourcing of raw ingredients, including hazelnuts, sugar, cocoa powder, palm oil, skim milk powder, and vanillin. These ingredients are delivered to Nutella factories in massive quantities, requiring large-scale handling infrastructure. Hazelnuts, one of the key components of Nutella, are often sourced from Turkey and Italy, two of the largest hazelnut producers in the world. Upon arrival at the factory, hazelnuts are stored in enormous silos or temperature-controlled storage rooms to maintain their freshness. The silos are made of food-grade stainless steel and designed to protect the nuts from humidity and contamination, while allowing for precise dispensing into the production line. The first step in processing the hazelnuts is cleaning. Hazelnuts arrive in bulk shipments, often mixed with debris such as shells, stems, and dirt. To address this, the factory uses a series of cleaning systems that include vibrating screens, air classifiers, and magnetic separators. The vibrating screens shake the nuts to separate them from larger debris, while the air classifiers blow away lightweight impurities like husks and dust. Magnetic separators are also used to detect and remove any metallic particles that might have entered the shipment during harvesting or transport. Once cleaned, the hazelnuts undergo visual inspection using high-speed optical sorting machines equipped with cameras and sensors. These machines identify and remove any defective hazelnuts, such as those with discoloration, cracks, or signs of mold. After cleaning, the hazelnuts move to the roasting stage. Roasting is a crucial step in developing the rich, nutty flavor that characterizes Nutella. In the factory, this is achieved using massive industrial roasting ovens. These ovens are designed with rotating drums or conveyor belts to ensure even roasting. The temperature is carefully controlled, typically ranging between 280 and 320 degrees Fahrenheit, depending on the size and moisture content of the hazelnuts. Sensors monitor the temperature and time to ensure consistency, as over-roasting can lead to bitterness, while under-roasting can result in a lack of flavor. The entire roasting process is automated, and the equipment is designed for continuous operation to handle the high volume of hazelnuts required for production. Once roasted, the hazelnuts are transferred to grinding machines. These machines are equipped with heavy-duty stainless steel blades and rollers that crush the nuts into a fine paste. The grinding process occurs in multiple stages, with each stage further reducing the particle size of the hazelnut paste. In the initial stage, the nuts are coarsely ground into a chunky paste. In the subsequent stages, the paste is refined into a smooth consistency, with particle sizes measuring less than 30 microns. This ultra-fine grinding is essential for achieving Nutella's creamy texture. The equipment used in this process, such as colloid mills and ball mills, is highly specialized and designed to operate under high pressure and at precise speeds. The resulting hazelnut paste is collected in large stainless steel tanks, where it is stored at a controlled temperature to preserve its flavor and consistency. While the hazelnut paste is being prepared, the other ingredients are processed in parallel. Sugar, which provides sweetness to Nutella, is delivered to the factory in bulk containers or tankers. Upon arrival, the sugar is unloaded into silos equipped with pneumatic conveying systems. These systems use air pressure to transport the sugar from the silos to the milling area, where it is ground into a fine powder. Industrial sugar mills are used for this purpose, and the grinding process ensures that the sugar particles are small enough to dissolve uniformly in the mixture. The factory also incorporates sieving systems to filter out any impurities or oversized sugar particles before they proceed to the blending stage. Cocoa powder, another key ingredient, undergoes a similar process. The cocoa powder is stored in sealed silos to protect it from moisture and contamination. Before being added to the Nutella mixture, the cocoa powder is sifted through vibrating screens to break up clumps and ensure a fine, even consistency. This step is crucial for achieving the smooth texture of the final product, as any clumps could create inconsistencies during blending. Palm oil, which gives Nutella its creamy consistency and prevents separation, is stored in large, temperature-controlled tanks. These tanks are equipped with heating elements to keep the oil in a liquid state, as palm oil tends to solidify at room temperature. The oil is pumped through insulated pipes to the mixing area, where it is carefully measured and added to the blend. The precise control of temperature and flow rate is essential to ensure that the oil integrates smoothly with the other ingredients. Skim milk powder, which adds a subtle dairy flavor and contributes to the creamy texture of Nutella, is stored in sealed containers or silos to prevent exposure to air and moisture. Before being used, the milk powder is sifted and screened to remove any lumps. Factories use advanced pneumatic conveying systems to transport the milk powder from the storage silos to the mixing area, ensuring that the ingredient is handled efficiently and hygienically. The blending process is the heart of Nutella's production, where all the prepared ingredients come together to form the final product. The blending tanks used in Nutella factories are massive, often with capacities of several thousand gallons. These tanks are equipped with high-speed agitators and temperature control systems. The hazelnut paste, sugar powder, cocoa powder, skim milk powder, palm oil, and vanillin are added to the tank in precise proportions, which are controlled by computerized dosing systems. These systems are programmed to weigh and dispense each ingredient accurately, ensuring consistency across batches. During blending, the mixture is heated slightly to help the ingredients combine more effectively. The temperature is carefully monitored, as excessive heat could alter the flavor and texture of the product. The blending tanks are designed to ensure even mixing, with agitators that create a vortex to incorporate all the ingredients thoroughly. The result is a homogeneous mixture with a smooth, creamy consistency. Once the blending process is complete, the mixture undergoes a refining stage. Refining is a critical step that ensures the final product is free of any graininess. The refining process takes place in multi-stage roller mills, which are equipped with heavy-duty steel rollers. These rollers apply immense pressure to the mixture, reducing the particle size of any remaining solids to less than 20 microns. This process not only enhances the texture of Nutella, but also improves its spreadability. The roller mills are fitted with precision sensors that monitor the pressure and temperature during refining, ensuring optimal performance. After refining, the mixture is transferred to the conching stage. Conching is a process borrowed from chocolate manufacturing and involves agitating the mixture in large, heated tanks for several hours. This process helps to further smooth the texture and enhance the flavor of the spread by allowing volatile compounds to evaporate and by evenly distributing the fats and solids. The conching tanks are equipped with paddles or rollers that knead the mixture continuously. The temperature and duration of conching are carefully controlled, as over-conching could negatively affect the spread's consistency. The finished Nutella is then pumped into holding tanks, where it is kept at a controlled temperature until it is ready for packaging. These tanks are equipped with agitators to prevent separation and maintain the spread's uniformity. Before the Nutella is packaged, it undergoes a final round of quality control. Samples from each batch are tested for flavor, texture, color, and viscosity. The factory uses advanced laboratory equipment such as viscometers and spectrophotometers to ensure that the product meets the company's stringent standards. Any deviations from the desired specifications are identified and corrected before the product proceeds to the packaging stage. Packaging is the final step in Nutella's production process, and it is carried out with the same level of precision and efficiency as the earlier stages. The spread is pumped from the holding tanks into automated filling machines, which dispense precise amounts of Nutella into jars. The filling machines are equipped with high-speed nozzles that can fill hundreds of jars per minute. Each jar is made from food-grade plastic or glass and arrives at the factory pre-sterilized to ensure hygiene. The jars are sealed with tamper-proof lids, which are applied and tightened using automated capping machines. Once the jars are sealed, they are conveyed to labeling stations, where Nutella's iconic branding is applied. The labels include important information such as the lot number, production date, and expiration date, which are printed using high-speed inkjet or laser printers. After labeling, the jars are inspected by vision systems that check for defects such as misaligned labels or damaged seals. Any defective jars are automatically removed from the production line. The jars are then packed into cardboard cartons using robotic packing systems. These systems are programmed to arrange the jars in specific configurations to maximize space and protect the jars during transportation. The cartons are sealed and stacked onto pallets using robotic palletizers. The pallets are then wrapped in plastic film for stability and loaded onto trucks or shipping containers for distribution. The entire packaging process is designed for high efficiency, with minimal manual intervention and maximum output. Throughout the factory, automation plays a key role in maintaining efficiency and consistency. Programmable logic controllers and supervisory control and data acquisition systems are used to monitor and control every aspect of the production process. These systems provide real-time data on parameters such as temperature, pressure, and flow rates, allowing operators to make adjustments as needed. The factory is also equipped with advanced robotics and machinery that ensure smooth operation, from ingredient handling to final packaging. Hygiene and safety are top priorities in Nutella factories. Production areas are constructed with food-grade stainless steel surfaces and epoxy-coated floors that are easy to clean and sanitize. Air filtration systems maintain a clean environment by preventing airborne contaminants from entering critical zones. Employees follow strict hygiene protocols, including wearing protective clothing and washing their hands regularly. The factory is regularly inspected to ensure compliance with international food safety standards, guaranteeing that every jar of Nutella is safe for consumption. This intricate, highly automated process ensures that Nutella is consistently smooth, flavorful, and delicious, meeting the high expectations of its millions of fans worldwide. Every step, from the handling of raw ingredients to the final packaging, is a testament to the engineering and precision that go into creating this beloved spread. The result is a product that continues to delight consumers, one jar at a time. Peanut butter, a staple spread beloved worldwide for its creamy or crunchy texture, requires a sophisticated and highly organized manufacturing process to meet the demand for consistent quality and flavor. Behind every jar of peanut butter is an intricate factory process that starts with the raw peanuts and ends with precisely packaged jars ready for distribution. Let's take an in-depth look at the factory production process, exploring the machines, systems, and engineering techniques that make it all possible. The process begins with the sourcing of raw peanuts. These peanuts are typically grown in countries like the United States, China, India, and Argentina, which are among the largest producers of peanuts globally. Peanuts are harvested in vast quantities, cleaned and dried at their source before being shipped to peanut butter manufacturing facilities. Factories require a consistent supply of high-quality peanuts, and to ensure that the raw peanuts are often tested upon arrival for size, moisture content, and overall quality. This ensures only the best peanuts are used for processing. Upon arrival at the factory, peanuts are stored in massive silos or bins designed specifically for food products. These silos are constructed from food-grade stainless steel or coated steel to prevent contamination and ensure proper hygiene. Inside the silos, the peanuts are protected from moisture, pests, and temperature fluctuations. These storage systems are equipped with conveyor systems that efficiently transfer peanuts from the silos to the initial cleaning and processing stages. The first step in processing peanuts is cleaning. Even though peanuts are partially cleaned at their source, factories implement a rigorous cleaning process to ensure no foreign materials or impurities remain. Vibrating screens are used to remove debris such as dirt, stones, and small sticks. Air classifiers blow air through the peanuts to remove lighter debris such as peanut skins or husks. Magnets are also employed to extract any metallic impurities. Optical sorting machines equipped with cameras and sensors scan each peanut as it moves along a conveyor belt, automatically removing any defective peanuts, including those with discoloration, mold, or deformities. After the cleaning process, the peanuts proceed to the roasting stage. Roasting is a critical step in peanut butter production, as it develops the rich, nutty flavor that defines the final product. Factories use industrial roasting ovens to roast the peanuts at controlled temperatures. These ovens come in two main types: batch roasters and continuous roasters. Batch roasters are used for smaller production lines, while continuous roasters, which use conveyor belts to move peanuts through a heated chamber, are used for larger scale operations. The temperature in these roasters typically ranges from 300 to 350 degrees Fahrenheit. The roasting process is closely monitored with temperature sensors and automated control systems to ensure the peanuts are roasted evenly. If some peanuts are over-roasted, they can turn bitter, while under-roasted peanuts may lack flavor. The level of roasting can also be adjusted depending on whether the final peanut butter will have a mild or more robust taste. Once roasted, the peanuts are cooled to stop the cooking process. Cooling is achieved by passing the roasted peanuts through chambers with powerful fans or cool air blowers. This step is crucial because it prevents the peanuts from continuing to cook, which could lead to inconsistencies in flavor. Some factories also use a water spray system to rapidly cool the peanuts, though this is less common as it can add moisture to the product. The cooling systems are designed to operate continuously to keep pace with the output of the roasting ovens. With the peanuts roasted and cooled, the next step is to remove their skins and separate the kernels. Skin removal is done using blanching machines. These machines have rotating drums or abrasive rollers that rub the peanuts, causing the thin outer skin to flake off. Some systems use steam blanching, where the peanuts are exposed to high-pressure steam to loosen the skins before mechanical removal. After blanching, the peanuts pass through air classifiers that blow away the loose skins, leaving behind clean peanut kernels. Factories also use gravity separators to sort peanuts by size and density, ensuring that only uniform peanuts proceed to the grinding stage. Before grinding, the peanuts are inspected again for quality. This is done using high-speed optical sorters that ensure any remaining defective peanuts are removed. Factories often have automated weighing and proportioning systems at this stage to determine the exact amount of peanuts needed for each batch. This level of precision is crucial for maintaining consistency in the flavor and texture of the peanut butter. The grinding process is the heart of peanut butter production. The roasted peanuts are fed into industrial grinders, where they are crushed into a fine paste. This process happens in multiple stages, beginning with coarse grinding and followed by finer grinding. The equipment used for this includes hammer mills and roller mills, which are specifically designed to reduce the peanuts into small, uniform particles. In many factories, the particle size is reduced to less than 20 microns, which is smaller than the diameter of a human hair. Achieving such a fine consistency is essential for the creamy texture that many consumers expect from peanut butter. For crunchy peanut butter, the process is slightly different. In these cases, a portion of the peanuts is coarsely ground and set aside before the final blending stage. These larger peanut pieces are later mixed into the smooth paste to create the characteristic crunchy texture. To prevent the peanut butter from separating, stabilizers such as hydrogenated vegetable oils or palm oil are added during the grinding process. These oils help bind the natural peanut oils to the solid peanut particles, ensuring a smooth and stable product that doesn't separate in the jar. Salt and sugar are also added at this stage to enhance the flavor of the peanut butter. Factories use precision dosing systems to measure and add these ingredients in exact proportions, ensuring every batch has the same taste. After grinding, the peanut butter is sent through a mixing stage, where it is further blended in large stainless steel tanks equipped with high-speed agitators. This stage ensures that the stabilizers, salt, and sugar are evenly distributed throughout the peanut butter. These tanks are often heated slightly to keep the peanut butter at the right consistency for mixing. The temperature is carefully controlled, as overheating can alter the flavor or texture of the peanut butter. Once the mixing is complete, the peanut butter undergoes quality control checks. Samples from each batch are tested in an on-site laboratory for flavor, texture, and consistency. Advanced instruments, such as viscometers, are used to measure the viscosity of the peanut butter, ensuring it meets the desired standards. Factories also use particle size analyzers to confirm that the peanut butter's texture is smooth and uniform. These quality checks are critical, as even slight variations can impact the final product's appeal to consumers. The final step in the manufacturing process is packaging. The peanut butter is pumped from the mixing tanks to filling machines, where it is dispensed into jars. These filling machines are capable of handling thousands of jars per hour, ensuring high efficiency. The jars, typically made of food-grade plastic or glass, arrive at the factory pre-cleaned and are sterilized again before filling. The filling nozzles are designed to dispense precise amounts of peanut butter into each jar, ensuring uniform weight and volume. Once the jars are filled, they move to the capping machines, where tamper-proof lids are applied and tightened. After capping, the jars are conveyed to labeling machines, which apply the brand's signature labels, along with lot numbers and expiration dates for traceability. Vision systems inspect each jar to ensure that the labels are correctly applied and that there are no defects in the seals or packaging. The jars are then packed into cardboard boxes using robotic packing systems. These robots are programmed to arrange the jars in specific configurations to optimize space and protect the jars during transportation. The boxes are sealed and stacked onto pallets using automated palletizing systems. Finally, the pallets are wrapped in plastic film for stability and loaded onto trucks or shipping containers for distribution. Throughout the entire production process, automation plays a vital role in maintaining efficiency and consistency. Factories are equipped with programmable logic controllers, PLCs, and supervisory control and data acquisition, SCADA systems, that monitor and control every aspect of production. These systems provide real-time data on parameters such as temperature, pressure, and flow rates, allowing operators to make adjustments as needed. Robotic systems handle many tasks, from sorting and cleaning peanuts to packaging the final product, reducing the need for manual labor and ensuring precision. Hygiene and safety are also top priorities in peanut butter factories. The production areas are constructed with food-grade stainless steel surfaces and epoxy-coated floors that are easy to clean and sanitize. Positive air pressure systems prevent airborne contaminants from entering critical zones, while strict hygiene protocols ensure that employees maintain cleanliness throughout the production process. The entire facility is regularly inspected to comply with international food safety standards, ensuring that every jar of peanut butter is safe for consumption. Peanut butter production is a complex and highly technical process that relies on advanced machinery, precise engineering, and rigorous quality control. From the cleaning and roasting of peanuts to the grinding, mixing, and packaging of the final product, every step is designed to create a spread that is smooth, flavorful, and consistent. Factories operate with remarkable efficiency, producing thousands of jars per day to meet the global demand for this versatile and beloved product. Strawberry jam production is a fascinating and highly engineered process that combines precision machinery with time-tested techniques to create a smooth, fruity spread. At the core of this process are high-quality strawberries, sugar, pectin, and citric acid, all carefully handled and processed to achieve the perfect consistency and flavor. Inside a modern jam factory, every step is optimized for efficiency, consistency, and food safety. The process begins with the selection and delivery of fresh or frozen strawberries. Factories typically source strawberries from local farms or large-scale suppliers. Frozen strawberries are often preferred for large-scale production because they are preserved at peak ripeness, ensuring consistent flavor year-round. The strawberries arrive in bulk containers and are stored in cold rooms or freezers to maintain their quality until processing begins. Before entering the production line, the fruit undergoes a thorough cleaning process. This includes washing the strawberries in large tanks filled with filtered water, where gentle agitation removes dirt, debris, and any residual pesticides. Once cleaned, the strawberries pass through optical sorting machines. These machines use cameras and sensors to identify and remove defective or discolored fruit. Advanced systems can even detect minute imperfections, ensuring that only the highest quality strawberries make it into the jam. After sorting, the strawberries are sent to cutting or mashing machines, depending on the desired jam texture. For chunkier jams, strawberries are coarsely chopped, while for smooth spreads, they are mashed or pureed into a uniform consistency. The fruit then enters large stainless steel cooking kettles or continuous cooking systems. In these vessels, the strawberries are combined with sugar, which not only sweetens the jam, but also acts as a natural preservative. The sugar is added using automated dosing systems that measure precise quantities to ensure consistent flavor. Pectin, a natural thickening agent derived from fruit, is added to help the jam set. Citric acid is also incorporated to balance the sweetness and enhance the fruit's natural flavor. The mixture is slowly heated, with temperatures reaching up to 220 degrees Fahrenheit to activate the pectin and achieve the ideal gel-like consistency. During cooking, the jam undergoes constant agitation to prevent scorching and ensure even heating. Steam-jacketed kettles or vacuum cookers are often used, as they allow for rapid and uniform heating. Modern vacuum systems are particularly advantageous because they enable cooking at lower temperatures, preserving the fresh flavor and bright color of the strawberries. Throughout the cooking process, sensors monitor the temperature, pH levels, and viscosity of the jam, ensuring that the final product meets strict quality standards. Once the jam reaches the desired consistency, it is pumped through a series of filters to remove any seeds or large pieces if a smoother texture is desired. The finished jam is then transferred to filling machines. These machines dispense precise amounts of jam into sterilized glass jars or plastic containers. The jars are immediately sealed with tamper-proof lids to maintain freshness and prevent contamination. After sealing, the jars are passed through pasteurization tunnels, where they are briefly heated to destroy any remaining microorganisms. Finally, the jars are labeled, inspected, and packed into cartons using robotic packaging systems. The entire process is highly automated, ensuring efficiency and consistent quality, from the arrival of fresh strawberries to the delivery of jars to store shelves. This seamless blend of traditional cooking techniques and advanced technology ensures that every jar of strawberry jam is rich in flavor, perfectly textured, and safe for consumers to enjoy. In the massive production facilities where Reese's peanut butter cups are made, the process begins well before any chocolate is poured or any peanut butter is mixed. It starts with sourcing two critical ingredients: high-quality peanuts and specially formulated chocolate. The peanuts arrive at the plant in large, tightly sealed containers, having already undergone preliminary sorting at dedicated processing centers. However, the Reese's factory does not take any chances. Upon arrival, each shipment of peanuts is sampled and tested for aflatoxins, moisture content, and flavor quality. Only the best peanuts pass through to the next stage. The first critical transformation begins in the peanut roasting room, a cavernous area lined with continuous batch roasters. These machines look like giant horizontal drums that rotate slowly, while hot air circulates inside, ensuring each peanut is evenly toasted to bring out its natural oils and enhance flavor. Temperatures inside the roasters are tightly controlled, typically between 300 and 350 degrees Fahrenheit, and the roasting cycle can last anywhere from 10 to 30 minutes, depending on peanut size and desired roast level. Workers monitor color readings using optical sensors, making slight adjustments to the roast if necessary to achieve that signature Reese's flavor. Once roasted, the peanuts are transferred via conveyor belts to powerful cooling tunnels. Giant fans blow chilled, filtered air over the peanuts to halt the roasting process immediately, locking in the flavor profile. After cooling, the peanuts pass through a series of magnetic separators and vibrating screens to remove any foreign materials or remaining shell fragments, ensuring absolute purity. Next comes the grinding phase. The roasted peanuts are funneled into industrial grinders, massive machines equipped with heavy-duty steel plates that spin at high speeds. The first grind reduces the peanuts into a rough paste. Then a secondary, finer grind transforms the mixture into the silky, smooth peanut butter that will fill every cup. During grinding, small amounts of sugar, salt, and a plant-based emulsifier are added to stabilize the peanut butter and give it the slightly sweet, distinctly savory flavor that fans recognize instantly. The temperature is carefully managed during this phase, usually kept between 120 and 140 degrees Fahrenheit to ensure the oils remain stable and the texture remains creamy but not runny. The freshly made peanut butter is then pumped into enormous stainless steel holding tanks, where it is kept warm and agitated gently to maintain a consistent texture. These tanks are connected by sanitary piping to the production lines, allowing for seamless and hygienic movement of the peanut butter when it's time to fill the cups. Meanwhile, the chocolate preparation is already underway in a different section of the factory. Reese's uses a specially formulated milk chocolate blend that balances sweetness, cocoa flavor, and a creamy melt-in-the-mouth texture. Bulk chocolate arrives in the form of large solid blocks or liquid tanker shipments, depending on the factory's setup. If solid, the chocolate is first broken down in massive pre-melters, slowly heating it to around 110 degrees Fahrenheit to achieve a uniform, molten state. Once liquefied, the chocolate is pumped into tempering machines, sophisticated systems that cool and reheat the chocolate in a precise curve to stabilize the cocoa butter crystals. This tempering process is critical. It gives the finished cups their glossy appearance, firm snap, and excellent shelf stability. Now, with both chocolate and peanut butter ready, the cup assembly line begins. First, paper cup molds are automatically dispensed onto a continuously moving conveyor belt. High-speed chocolate depositor machines then squirt a carefully measured amount of molten chocolate into each paper cup, forming the base layer. The conveyor belt vibrates gently to help the chocolate settle evenly across the bottom and slightly up the sides of each mold. Immediately after this, the conveyor moves the cups through a cooling tunnel, where chilled air at around 50 degrees Fahrenheit partially solidifies the base chocolate layer. This quick cooling ensures that when the peanut butter is deposited, it won't sink all the way to the bottom of the cup, maintaining the ideal layered structure. Next, the creamy peanut butter is deposited into the center of each chocolate base using precision nozzles. The amount of peanut butter is meticulously controlled by programmable pumps, ensuring every Reese's cup has the same perfect peanut to chocolate ratio. Interestingly, the peanut butter filling itself is slightly cooler than the chocolate, typically around 80 to 90 degrees Fahrenheit, which helps it stay firm during the next stages of production. After the peanut butter is deposited, a second layer of molten chocolate is dispensed over the top, sealing in the peanut butter and forming the upper shell of the candy. Again, careful vibration of the conveyor ensures a smooth, even surface. At this point, visual inspection systems using high-speed cameras and AI algorithms scan the cups for consistency, checking fill levels, alignment, and any surface imperfections. Defective cups are automatically rejected from the line. The filled cups then pass through an extended cooling tunnel where they spend several minutes gradually chilling back down to around 45 degrees Fahrenheit. This staged cooling prevents the chocolate from blooming, a condition where cocoa butter rises to the surface and creates an unsightly white film. Instead, the cooling process locks in that deep, shiny chocolate sheen. Once fully cooled, the cups are ready for packaging. Automated robotic arms gently lift rows of finished Reese's cups and place them into pre-formed trays or directly onto flow wrapping machines. Each candy is enveloped in a thin, protective layer of branded orange packaging film. Heat sealers quickly fuse the edges of the wrapper shut, trapping a pocket of nitrogen gas inside. This inert atmosphere helps prevent oxidation, preserving freshness and flavor for extended shelf life. The wrapped candies are then grouped into multi-packs by high-speed cartoning machines, which fold and seal cardboard boxes around designated numbers of cups, whether it's a standard 2-pack, a king-size 4-pack, or a family-size bag of miniatures. These boxes are coded with manufacturing dates, lot numbers, and other traceability data before being stacked neatly onto pallets. Before the pallets leave the factory, a final quality control check is performed. Random packages are pulled from the line and subjected to a battery of tests, including weight checks, taste tests, visual inspections, and even X-ray analysis to ensure there are no contaminants or structural flaws inside the candies. Only when these samples pass inspection are the pallets shrink-wrapped and labeled for distribution. From there, the Reese's Cups embark on their journey through a highly coordinated supply chain. Pallets are loaded onto refrigerated trucks, kept at cool but not freezing temperatures to prevent the chocolate from melting or degrading. Distribution centers across the country receive the shipments, from which they are sent to grocery stores, convenience shops, vending machine suppliers, and even directly to online retailers. What's fascinating about the Reese's production process is how every detail, temperature, timing, movement, is optimized for both speed and quality. The factories are largely automated, with programmable logic controllers and centralized computer systems coordinating every phase, minimizing human error and maximizing consistency. Maintenance crews monitor the machinery continuously, ready to intervene if even the slightest deviation occurs. Yet, despite the heavy automation, a skilled team of chocolatiers, food scientists, and process engineers oversee operations daily, ensuring that the soul of the Reese's Cup, the perfect balance of creamy peanut butter and silky milk chocolate, is never compromised. In recent years, new technologies have further enhanced production. Advanced predictive maintenance uses AI algorithms to detect early signs of equipment wear, preventing costly downtime. robotic packaging systems have become faster and more flexible, adapting to different product formats with minimal reprogramming. Even energy efficiency has improved dramatically, with modern factories recapturing waste heat from the roasting and tempering processes to reduce overall power consumption. The result of all this effort is what you hold in your hand, a Reese's peanut butter cup with the same incredible taste that has delighted generations. From careful peanut selection to intricate chocolate tempering, from the first squirt of chocolate to the final seal of the wrapper, every step is a marvel of precision, engineering, and culinary artistry, ensuring that each bite delivers the unmistakable Reese's experience, time after time. The making of Hershey's milk chocolate begins long before any bars are molded or wrapped. It starts with sourcing one of the world's most essential commodities, cacao beans. Hershey's purchases massive quantities of cacao from regions like West Africa, Central and South America, and parts of Southeast Asia. Upon arrival at Hershey's specialized facilities, the cacao beans undergo strict quality control protocols. Sampling machines pull randomized beans from each shipment, checking for mold, contamination, fermentation quality, and flavor profiles. Only beans that meet Hershey's high standards proceed to production. The first major operation is cleaning. Beans travel through a series of shaking screens, magnetic separators, and powerful air jets that remove debris like sticks, stones, and dust. Once cleaned, the beans are routed to the roasting department. Here, colossal stainless steel drum roasters, each capable of handling thousands of pounds per batch, bring the beans up to roasting temperatures of around 250 to 300 degrees Fahrenheit. This roasting phase is crucial. It not only develops the rich cocoa flavors, but also loosens the shell from the nib, the part of the bean that will become chocolate. After roasting, the beans pass through cracking and winnowing machines. Heavy rollers crack the beans open, and powerful airflows then separate the lighter, papery shells from the heavier cocoa nibs. The nibs are collected and sent immediately into the refining phase. The shells, interestingly, don't go to waste. Many are repurposed as agricultural mulch or used in animal feed. The next transformation happens in the grinding rooms. Industrial grinders crush the nibs into a thick, gritty paste known as chocolate liquor. Despite its name, it contains no alcohol. Giant stone mills or modern ball mills spin tirelessly, reducing particle sizes to less than 100 microns. This grinding process releases the cocoa butter within the nibs, turning the dry nibs into a fluid, rich mass. At this stage, the chocolate liquor is either stored or immediately processed depending on the specific recipe being produced. For Hershey's signature milk chocolate, chocolate liquor alone is not enough. It must be blended with several other ingredients: sugar, milk, and cocoa butter, among others. Hershey's famously uses fresh condensed milk rather than powdered milk, a technique that imparts its distinctive flavor. Tankers bring in condensed milk that has already been pasteurized and quality tested for microbial safety. The milk is combined with sugar in large stainless steel kettles and cooked to form what is known as a milk crumb, a dry, sweet, caramelized powder that becomes the base for Hershey's milk chocolate. The milk crumb, chocolate liquor, and additional cocoa butter are blended together in massive mixers that resemble horizontal cement mixers but are built for food-grade standards. In these tumbling vessels, the blend of ingredients becomes a coarse chocolate dough. This dough is then fed through refining rollers, 5 or 6 massive polished steel rollers stacked horizontally. As the dough passes through each successive roller gap, it is compressed and sheared finer and finer, reducing the sugar and cocoa particles to just the right microscopic size to ensure a smooth texture. At this point, the chocolate still lacks the silky consistency and full flavor that people expect. That's where one of the most crucial steps in chocolate making enters: conching. Hershey's uses giant conching machines, massive, heavy-duty mixers with granite rollers that agitate, aerate, and warm the chocolate dough for hours. Traditional conching could take up to 72 hours, but with modern methods and specialized Hershey's technology, the time has been optimized without sacrificing quality. During conching, volatile acids and bitter flavors evaporate away, while cocoa and milk flavors mellow and deepen. At the same time, the continuous mixing further reduces any remaining coarse particles and disperses the cocoa butter thoroughly throughout the mass. Temperature control during conching is critical. The chocolate must stay within an exact range, typically between 130 to 180 degrees Fahrenheit, depending on the desired flavor development. Ventilation hoods draw off unwanted volatiles, and sensors embedded throughout the conches constantly report data back to automated control systems, adjusting speed and temperature as needed. Following conching, the chocolate moves into the tempering phase. Tempering is an art and science all its own. Chocolate is carefully cooled and reheated through specific temperature curves to create stable cocoa butter crystals. This gives finished chocolate its snap, gloss, and resistance to melting at room temperature. Hershey's uses continuous tempering machines, which can process thousands of pounds per hour. These machines use a series of heated and cooled zones to guide the chocolate through its crystal formation journey with pinpoint accuracy. Improper tempering would result in chocolate that's dull, crumbly, or prone to blooming, a white discoloration, so this step must be executed flawlessly. Once tempered, the liquid chocolate is transported through heated pipes to the molding stations. There, automated depositors squirt precise amounts of chocolate into endless arrays of molds, some shaped for classic Hershey's bars, others for miniature versions or seasonal specialties. The molds vibrate rapidly on oscillating tables to eliminate any air bubbles and ensure an even surface. The molds then enter a long cooling tunnel, a carefully calibrated environment where the chocolate solidifies slowly and evenly. Inside the tunnel, the temperature drops gradually from around 70 degrees Fahrenheit to about 50 degrees, preventing thermal shock and ensuring that the chocolate sets with a fine, smooth crystal structure. After cooling, the solid chocolate is demolded. High-speed mechanical arms flip and flex the molds, gently releasing the perfectly formed bars onto conveyor belts. At this stage, visual inspection systems equipped with high-speed cameras and AI check every piece for uniformity, detecting even minor surface defects or molding errors. Imperfect chocolates are removed from the line for recycling back into the production process. The next step is packaging. For Hershey's bars, the chocolate rides conveyors into flow wrapping machines. Each bar is enveloped in a tight sleeve of foil and then an outer branded paper wrapper. Modern flow wrappers work at astonishing speeds, often wrapping hundreds of bars per minute with perfect precision. The wrapped bars are coded with expiration dates, batch numbers, and tracking information to ensure full traceability from production through to sale. Once wrapped, the bars are collated into cartons or retail trays by robotic packers, which arrange them neatly in boxes that are then sealed, labeled, and stacked onto pallets. Before shipment, a random sample from every production batch undergoes additional quality assurance tests, including break tests, melt tests, taste panels, and microbial analysis. Only after passing all these checks are the pallets released for distribution. The finished Hershey's milk chocolate bars then enter the logistics phase, moving through regional distribution centers that coordinate delivery to supermarkets, convenience stores, cinemas, and countless other retailers around the world. Throughout the distribution chain, temperature control remains critical. Warehouses and trucks are climate controlled to prevent the bars from experiencing temperature swings that could cause chocolate bloom or textural changes. Throughout the entire factory process, Hershey's leverages advanced automation, continuous monitoring, and decades of chocolate-making expertise to ensure that every bar tastes as iconic and consistent as the last. The level of control is extraordinary. Chocolate viscosity, particle size distribution, moisture levels, and flavor profiles are measured and adjusted in real time using sophisticated inline sensors and laboratory tests. In recent years, Hershey's has also invested heavily in sustainability, working directly with cocoa farmers through its Cocoa for Good program to promote ethical sourcing, better farming practices, and environmental stewardship. This commitment ensures not just the continued availability of high-quality cacao, but also a better future for the communities that produce it. The journey of a Kit Kat begins with two major components: the chocolate coating and the crisp wafer core. Both are manufactured separately and in parallel streams before being married together into the unmistakable Kit Kat form. Each ingredient, each layer, and each step is engineered with astonishing precision to create the perfect snap, crunch, and creamy finish that Kit Kat is famous for. The process starts with the preparation of the chocolate. Kit Kat's signature coating is slightly different from pure chocolate. It is technically a compound chocolate, specially formulated to give a smooth melt and quick setting properties ideal for enrobing wafers. At factories like Nestlé's York facility in the UK or similar plants worldwide, bulk cocoa liquor, cocoa butter, sugar, and milk solids are combined. The cocoa beans that form the basis of the liquor are sourced from sustainable suppliers, cleaned, roasted, and ground into fine paste months before production even begins. To prepare the chocolate coating, the cocoa liquor is blended with sugar and powdered milk in enormous stainless steel mixers. This mixture is then refined through a series of precision-calibrated rollers, reducing the particle size to around 20 microns, finer than the human tongue can detect. The refining phase is essential to create the smooth mouthfeel Kit Kat lovers expect. Following refinement, the chocolate mass moves into conching machines, where it is slowly mixed, aerated, and heated. This removes any bitter flavors and unwanted acidity, while promoting the development of a creamy, caramel-like flavor that defines Kit Kat's chocolate. Temperature control during conching is rigorously maintained at around 135 to 180 degrees Fahrenheit, depending on the recipe. Once the chocolate reaches the right flavor and viscosity, it is moved into tempering units, where it's carefully cooled and reheated to produce stable cocoa butter crystals. Proper tempering ensures that the finished chocolate will have a shiny appearance, a satisfying snap, and resistance to blooming. Meanwhile, in another section of the factory, the production of the wafer sheets is underway. Wafer batter, made from a simple mixture of wheat flour, sugar, vegetable oil, leavening agents, and water, is mixed in giant, computer-controlled vats. The batter is pumped through piping systems directly to high-speed wafer baking ovens, each stretching tens of meters in length. These wafer ovens consist of two continuously moving steel belts that sandwich the batter and pass through a baking tunnel. As the belts travel, radiant heat, conduction, and convection work together to bake the batter into ultra-thin, crisp wafer sheets. Each sheet emerges from the oven perfectly cooked, around 2 to 3 millimeters thick, with a delicate, light texture and a uniform golden brown color. After baking, the wafer sheets are rapidly cooled, using forced chilled air to prevent moisture absorption. They are stacked and transported via conveyor belts to the cream spreading stations. Here, a thin layer of specially formulated filling, a mixture typically based on ground wafer crumbs, vegetable fats, sugar, and milk solids, is evenly spread across the wafers. The filling not only enhances the flavor, but also acts as a structural adhesive, bonding the multiple wafer layers together. Usually, 3 or 4 wafer sheets are stacked, with cream filling between each layer. These multi-layered blocks are then pressed under controlled pressure to ensure perfect bonding without cracking or crushing the delicate wafers. After resting for stabilization, the wafer blocks are transferred to high-speed cutting machines. The cutting process is a masterpiece of mechanical precision. Using laser guides and ultrasonic blades, the blocks are sliced first longitudinally, then crosswise into the familiar slim Kit Kat finger dimensions. Every cut must be perfect. Any deformation could later disrupt the enrobing process or spoil the iconic snap experience. Once cut, the wafer fingers are ready for enrobing. Conveyors carry them through a chocolate waterfall inside the enrobing machines. A curtain of tempered Kit Kat chocolate cascades over the wafers, completely coating them on all sides. Excess chocolate is blown off the bottom with controlled air jets, creating the thin chocolate layer underneath that gives Kit Kat its balanced chocolate to wafer ratio. Directly after enrobing, the fingers pass through a vibrating section of the conveyor to settle the chocolate coating and eliminate air bubbles. They then enter a series of cooling tunnels where cold, dry air, typically kept between 40 and 50 degrees Fahrenheit, slowly solidifies the chocolate coating without causing condensation, which would ruin the texture. At this point, the individual fingers are grouped together. Kit Kat is traditionally made with 4 fingers to a bar, although mini versions, single fingers, and chunkier variants are also produced. Robotic arms align and group the fingers with exact spacing between them before feeding them into wrapping machines. Kit Kat's iconic red and white wrapper is a masterpiece of branding and practical design. Wrapping is done using ultra-fast flow wrappers that synchronize perfectly with the grouping conveyors. Each set of fingers is enveloped in foil or a plastic laminate film, which protects against moisture and oxygen while maintaining the crunch of the wafer and the smoothness of the chocolate. The wrapping machines heat seal the edges at high speed, and rollers gently press and fold the sealed packs for that crisp, tight package finish Kit Kat is known for. As the wrapped bars move down the line, high-speed scanners and cameras inspect each package for correct seal integrity, label placement, and print clarity. Imperfections are detected in milliseconds, and defective packs are automatically ejected into collection bins for recycling. Once the Kit Kats are individually wrapped, the next stage is boxing and palletizing. Robotic case packers arrange the wrapped bars into boxes or display cartons, which are then sealed with automatic tapers and labeled with tracking information. Each box is carefully weighed and scanned to ensure it matches target specifications before being stacked onto pallets by robotic arms or palletizing machines. Throughout the entire production process, rigorous quality control is applied at every major step. Samples of chocolate, wafer batter, finished wafers, and completed bars are pulled at regular intervals for lab analysis. These tests include moisture content checks, microbiological safety testing, taste panels, and break strength tests to ensure the classic crisp break of a Kit Kat remains perfect batch after batch. In addition to inline testing, larger batch samples are subjected to accelerated aging studies to simulate how the product will perform over its shelf life. Sensory evaluation booths, staffed by trained taste testers, ensure that every batch maintains the exact flavor, aroma, texture, and mouthfeel that consumers expect. Once the Kit Kats are boxed and palletized, they are shipped out from climate-controlled distribution centers. Transport conditions are carefully managed to prevent temperature fluctuations that could cause chocolate bloom or wafer softening. Many shipments are refrigerated during summer months or in hotter climates to guarantee the product arrives in prime condition. Kit Kat's industrial production is a brilliant choreography of automation, sensory science, and quality management. Despite the high level of automation, human oversight remains crucial. Line operators monitor critical control points, adjust machine settings, respond to alarms, and carry out maintenance to keep the lines running smoothly, often 24 hours a day, 7 days a week. Recent advancements have further refined the process. State-of-the-art production lines now incorporate AI-driven predictive maintenance, allowing engineers to anticipate mechanical failures before they happen. Machine learning algorithms also optimize ingredient mixing, cooking times, and cooling profiles, subtly adjusting for real-time variables like humidity, ingredient lot variation, or slight temperature shifts in the facility. KitKat's commitment to sustainability is woven into production as well. Modern factories are equipped with energy recovery systems that reuse heat from the ovens and chillers. Water used in cooling and cleaning processes is recycled wherever possible. Additionally, KitKat's cocoa is 100% sourced through programs like Rainforest Alliance certified farms, ensuring ethical and environmentally responsible cocoa farming practices. Each KitKat bar that makes it into a consumer's hands is the end product of thousands of micro decisions and perfectly tuned processes: baking, layering, cutting, coating, cooling, wrapping, all executed with a level of precision that would make a Swiss watchmaker proud. The crisp snap of the break, the lightness of the wafer, the creamy melt of the chocolate. Every detail is the result of decades of research, refinement, and relentless pursuit of chocolate and wafer perfection. In a modern Oreo manufacturing facility, key dry ingredients are delivered in bulk, often by rail cars or food-grade trucks, and are pneumatically conveyed into large storage silos made of stainless steel or epoxy-lined carbon steel. These silos are sealed from air and moisture and are connected to the factory's central control system. The main dry ingredients include unbleached, enriched wheat flour, processed cocoa powder, granulated sugar, and minor dry components like baking soda and salt. Each of these materials is handled in its own silo or hopper, and automated augers or vibratory feeders dispense precise quantities into batch weighing hoppers. These hoppers sit on load cells, sensitive scales that can measure down to a fraction of a gram. This is essential because the correct ratio of flour to cocoa to sugar directly affects not only the flavor, but also how the dough behaves under pressure during molding. If the cocoa content is even slightly too high, for instance, the dough may become too brittle and crack during forming. If it's too low, the wafers may bake up too soft, losing the crisp snap that defines an Oreo. Once the dry materials are batched, they are conveyed into a pre-mixing chamber. At this stage, powdered ingredients are briefly tumbled together to ensure initial homogeneity before liquids are added. Then it's time for the liquid components to enter the system. These include vegetable shortening, often a blend of palm and canola oil, along with a sugar syrup or glucose solution, invert sugar, lecithin, and vanillin or other flavoring agents. The fats and liquids are stored in temperature-controlled tanks and are metered into the mixer through heated pipes. The temperature of the fats is critical. Too cold, and they won't disperse evenly. Too hot, and they could melt too aggressively, breaking down the emulsion and affecting dough integrity. All of these components are combined in large jacketed horizontal mixers or double sigma arm batch mixers. These mixers are chosen for their ability to handle heavy, cohesive doughs while still ensuring thorough dispersion. Inside the mixer, paddles or blades knead the dough continuously, folding and stretching it to develop a uniform texture. The mixer operates under a specific time and speed profile, starting slow to incorporate the dry and wet components, then increasing speed to blend, then finishing with a gentle knead to avoid overworking the dough. The goal here is a dough that's soft but not sticky, cohesive but not tough. Sensors inside the mixing chamber monitor temperature and torque, two key indicators of dough readiness. If the dough becomes too warm from friction, it can become greasy and difficult to form clean edges in the molding machines. If it's undermixed, the ingredients won't be uniformly distributed, and inconsistencies in cookie size, color, and bake profile will result later on. Once the dough reaches its target specifications, it's discharged from the mixer through a hydraulically controlled trapdoor at the base of the mixing tank. The dough falls into a dough transport system, typically a set of conveyors or troughs lined with non-stick materials like Teflon or food-grade UHMW polyethylene. At this stage, the dough may still be slightly warm, around 30 degrees Celsius to 35 degrees Celsius, and has a dense, matte appearance with a strong cocoa aroma. Before moving to the forming machines, the dough must undergo a resting period in certain operations. This allows the flour to fully hydrate and any residual gases or trapped air to escape. In high-speed production environments, however, this rest period may be minimized or skipped altogether if the formulation is optimized for immediate processing. This completes the initial phase: ingredient intake, formulation, mixing, and dough discharge. Each step up to this point is carefully controlled by recipe management software that ensures no human error can affect batch consistency. Recipe locks, scanner-based operator identification, and redundant scale verification ensure each batch of Oreo wafer dough is made precisely to the specifications required to perform flawlessly in the next stage of the journey: shaping and embossing. Now that the chocolate wafer dough has been prepared with absolute precision, measured, mixed, and conditioned, it moves into one of the most visually iconic and mechanically fascinating phases in the Oreo production line: forming and molding. This step takes the dense, cocoa-rich dough and transforms it into thousands of uniformly sized, detailed cookie wafers, each embossed with the distinctive Oreo pattern. This is not simply cutting shapes out of dough, it's a highly engineered, high-speed process where consistency in shape, thickness, and surface detail must be maintained across millions of units every day. The freshly prepared dough is conveyed to a hopper positioned above a sheeter. This sheeter is a wide, stainless steel roller assembly that flattens the dough into a uniform sheet of specific thickness. The dough moves between a set of rollers, typically 2 or more steel cylinders calibrated to exact tolerances that compress it to the target height. For Oreo wafers, the final sheet is quite thin, often around 3 to 4 millimeters, with a consistent density and moisture distribution. Getting this thickness right is critical. If the sheet is too thick, the cookie may not bake evenly or could become too brittle. Too thin, and the cookies may crack, burn, or crumble during sandwiching. Sensors measure the thickness of the sheet continuously using laser or ultrasonic gauges. If deviations are detected, servo-driven actuators automatically adjust roller spacing to maintain precision. The sheeter also includes edge trimmers, small, motorized blades that cut off uneven or frayed edges of the dough sheet to keep the line uniform. The trimmed edges are collected by a scrap recovery system and reintroduced into the mixing system, minimizing waste without compromising freshness or quality. Once the dough sheet is perfected, it enters the rotary molder. This machine is central to the Oreo brand's identity, as it forms the shape, size, and embossed design of each cookie wafer. The rotary molder consists of 2 primary components: a rotating die roller and a pressure roller. The die roller is a cylindrical drum engraved with multiple cavities, each one precisely carved with the Oreo design. These cavities aren't just cosmetic. Their depth and contour dictate the final relief of the cookie surface. As the dough sheet passes between the die roller and pressure roller, each cavity punches into the dough, compressing it into shape and imprinting the Oreo design. The pressure roller, covered in food-safe rubber or polymer, pushes the dough up into the die cavities, ensuring a clean, complete mold. As the die drum continues rotating, the shaped wafers are extracted by a combination of mechanical pushes and vacuum assist systems, which gently remove the cookies from the cavities without smudging the design. These freshly molded cookie wafers are then transferred onto a wide mesh conveyor belt in a continuous, uninterrupted line. Each wafer is spaced evenly to allow for proper airflow in the next phase, baking. Meanwhile, the excess dough surrounding the cutouts, known as webbing, is carefully separated and sent back through the scrap system. This recovery loop is highly efficient, capturing nearly 100% of the unused dough and returning it to the mixer via chilled transport belts. To ensure product consistency, reworked dough is blended at a fixed percentage into fresh dough, preventing any changes in texture, flavor, or moisture that might result from overprocessing. As the line of uniform, molded Oreo wafers advances, they approach the baking tunnel, one of the most thermodynamically sophisticated parts of the facility. The tunnel oven is a massive structure, often exceeding 30 meters in length, segmented into multiple temperature-controlled zones. Each zone is precisely tuned to manage the gradual dehydration and expansion of the cookie, ensuring even baking from edge to center. The ovens use convection, conduction, and in some cases, radiant heat, depending on the equipment manufacturer and regional factory specifications. The cookie wafers bake as they travel slowly through the tunnel, typically for a duration of 4 to 6 minutes. Conveyor speed, airflow rate, and internal oven temperatures are continuously adjusted via programmable logic controllers that interface with sensors monitoring internal humidity, surface temperature, and even color of the baking cookies using infrared imaging systems. The target bake is one where the cookie becomes crisp and fully set while retaining a slight moisture gradient at its core, enough to ensure it sandwiches cleanly without shattering, and holds up in milk without becoming soggy too quickly. Another crucial parameter monitored at this stage is cookie spread and diameter. Because the molded wafers expand slightly as they bake, their final size must fall within a fraction of a millimeter to ensure they'll match perfectly with their paired half during sandwiching. Edge blowout, where cookies develop uneven bulges or bubbles, is prevented by careful control of initial dough temperature, mold compression depth, and oven humidity during the first baking phase. As the cookies exit the oven, they are immediately passed through a staged cooling system. This phase is designed to gently bring the cookies from their internal post-bake temperature of roughly 160 degrees Celsius down to ambient room temperature. Cooling too quickly can cause the wafers to crack, warp, or experience checking, tiny surface fractures that affect aesthetics and structural integrity. To avoid this, the conveyor slowly moves the wafers through a series of cooling zones with progressively decreasing airflow temperatures. High-volume fans push filtered, dehumidified air over the wafers in a cross-flow pattern that cools them evenly on all sides. By the time the wafers reach the end of the cooling tunnel, they are firm, crisp, and at a stable moisture level, typically around 1.5% to 2%. This ensures maximum shelf life, a satisfying crunch, and ideal compatibility with the creme filling in the next phase of production. They are now ready for alignment and pairing. Wafers are automatically aligned into dual streams using diverters and channeling guides. Conveyor belts, equipped with vision systems, scan for defects such as missing embossing, chips, discoloration, or breakage. These systems use high-speed cameras and AI-assisted pattern recognition to detect any imperfections in milliseconds. Rejected cookies are diverted to a waste collection hopper, and approved wafers continue forward to the sandwiching stage. With the Oreo chocolate wafer cookies fully formed, baked, and cooled, the production line now transitions into one of the most iconic and mechanically synchronized parts of the process: sandwiching. This stage involves the precise alignment of two delicate wafer halves around a carefully deposited swirl of creme filling, forming the complete Oreo cookie as we know it. What may seem like a simple task, placing filling between two cookies, is in fact a highly controlled and technically advanced process that prioritizes speed, accuracy, hygiene, and product consistency. The cooled wafers arrive at the sandwiching station via dual-lane conveyors that separate and feed cookies into two different orientations: bottom wafers and top wafers. The bottom wafers are destined to receive the cream filling, while the top wafers are held back momentarily, synchronized to arrive just as the filling has been deposited. Vision-guided pick-and-place arms or mechanical guides ensure that each cookie is properly positioned and oriented with the embossed design facing upward, especially important for branded recognition in the final presentation. The placement needs to be exact. Even a slight misalignment could result in uneven sandwiching or a crooked creme center, which would be rejected downstream. At the heart of the sandwiching line is the creme depositor. This component is engineered to dispense a precise amount of creme onto the center of each bottom wafer. The creme filling itself has been prepared earlier in the process and is stored in stainless steel holding tanks near the sandwiching line. The base creme is a blend of vegetable shortening, powdered sugar, and natural or artificial flavorings, aerated to achieve a smooth and creamy texture. It is kept at a controlled temperature, typically between 25 degrees Celsius and 30 degrees Celsius, to maintain flow consistency without being too runny or too firm. The creme is pumped into the depositor through a jacketed delivery line, which maintains temperature and prevents any hardening or separation. Inside the depositor, a rotary valve system or piston-driven nozzles release measured quantities of filling in circular swirls directly onto each passing wafer. The target deposition amount is extremely precise, usually around 3 grams per cookie for the original Oreo. For double stuff, the system is calibrated to deliver twice that volume, and the depositor nozzle height is adjusted accordingly to accommodate the larger swirl. The deposition speed is synchronized with the conveyor, meaning each swirl is deposited while the bottom wafer is in motion. To maintain consistent swirl shapes, the nozzle spins at a high RPM as it dispenses the cream. Sensors and imaging software track swirl size, height, and position. If the deposit strays from the central zone or falls outside weight tolerances, that cookie is automatically flagged and diverted. These sensors run continuously, sampling thousands of cookies per minute with extremely tight thresholds for variance. Once the creme is in place, the top wafer is gently placed onto the swirl. This is done by an overhead transfer arm or drop chute designed to lower each top cookie into place with just enough pressure to make contact without squashing the filling. The timing here is critical. Placing the top wafer too early could create smearing or incomplete adhesion, while placing it too late could allow the creme to set and result in a loosely held sandwich. Once the two halves make contact, a calibrated compression roller or paddle gently presses them together to create a uniform sandwich with a visible, even creme edge. The newly assembled Oreo cookies are then conveyed forward to undergo another round of quality inspection. At this stage, high-speed vision systems again scan for defects. These include cracked or broken wafers, misaligned sandwiches, off-center cream, or excess filling that has oozed out past the edges. Cookies that fail to meet standards are ejected via pneumatic pushers or retractable gates, landing in separate bins for non-conforming product. These rejected cookies are either discarded or recycled depending on factory policies and whether they passed earlier food safety checks. The good cookies move on to the next major phase, cooling and setting. Even though the creme filling is solid at room temperature, the act of depositing and sandwiching generates residual warmth, and the filling remains somewhat malleable for several minutes. To stabilize the sandwich structure and ensure long-term integrity during packaging and shipping, the cookies are passed through a controlled cooling tunnel. This tunnel gradually brings the product's temperature down to a stable point, typically just below ambient, which firms up the cream and locks in the sandwich's structural cohesion. As cookies exit the cooling tunnel, they are directed toward the packaging line. Here, the cookies are grouped and arranged into stacks or rows depending on the intended package format, whether it's a classic tray-style retail pack, a resealable pouch, a single serving sleeve, or a multi-pack unit. For traditional packs, the cookies are guided into channels that group them into stacks, typically of 3 or more, which are then lowered into thermoformed plastic trays by robotic pick-and-place units. These trays help protect the cookies from damage and keep them organized for end-user convenience. Parallel to this, packaging film, pre-printed with branding, nutritional labels, and product information, is unwound from large rolls and fed into a form-fill seal machine. As the cookie-filled trays pass through the machine, the film is wrapped around the product, heat-sealed on all sides, and trimmed to size. Oxygen scavengers or desiccants may be inserted for freshness in some markets, depending on climate and shelf life requirements. For resealable packs, a Ziploc or peel-back adhesive strip is applied as part of the film sealing process, ensuring that consumers can open and close the package without reducing freshness. Each package unit is printed with a lot number, manufacturing date, facility code, and expiration date using high-speed thermal inkjet or laser printers. These codes enable full traceability and are cross-referenced with the production batch data stored in the factory's ERP system. From mixing and molding to creme filling and sealing, every step of the process can be traced back to specific machines, operators, shift schedules, and ingredient batches, an essential feature for food safety compliance and recall readiness. Once sealed, packages are conveyed to automated case packers. Here, robotic arms load the wrapped units into corrugated cardboard cartons, which are then glued or taped shut. These cartons are palletized according to preset patterns that optimize load stability and cube efficiency for shipping. Pallets are wrapped with stretch film, labeled with shipping barcodes and inventory data, and routed to the warehouse staging area. At this point, the Oreo cookies have completed their physical transformation from separate cocoa wafers and creme filling into a polished, fully packaged, ready-to-ship product. But before they leave the factory, they undergo a final quality audit. Samples from each batch are pulled from the finished goods line and tested by in-house sensory panels and laboratory staff. Taste, texture, aroma, appearance, and moisture content are evaluated to ensure that the product not only looks perfect, but delivers the consistent flavor and mouthfeel that Oreo is known for. Moisture levels are especially critical. Too high, and the cookie can lose its crispness during storage. Too low, and it can become brittle or stale. Texture analyzers apply mechanical pressure to the cookies to evaluate crunch resistance and breaking force, while gas chromatography is used to verify flavor compound profiles. Packaging integrity tests include drop tests, seal strength verification, and temperature cycling simulations that mimic transport and storage conditions across various markets. Once these final inspections are passed, the cookies are released for distribution. Pallets are loaded into climate-controlled trucks or containers, routed through regional distribution centers, and ultimately arrive at retail outlets, vending networks, or direct-to-consumer channels. With the Oreo cookie now fully assembled, inspected, packaged, and palletized, the final phase of the in-factory process is dedicated to the logistics, storage, inventory control, and outbound quality assurance systems that prepare the product for global distribution. While it may seem like the technical complexity is behind us, this stage involves its own set of sophisticated workflows designed to ensure that every package remains pristine, traceable, and shelf-stable for months after production, regardless of whether it ends up in a small, rural convenience store or a high-volume urban supermarket. The finished pallets of Oreos are moved from the end-of-line palletizing systems into a dedicated finished goods warehouse. This space is part of the factory complex, but isolated from production to prevent cross-contamination and maintain temperature and humidity stability. Oreo cookies, especially those with creme fillings, are highly sensitive to environmental changes. Excessive heat can soften the filling or compromise the packaging seal, while high humidity can cause moisture migration into the wafer, leading to loss of crispness. To combat these risks, the warehouse is maintained at a tightly regulated temperature, typically between 18 degrees Celsius and 22 degrees Celsius, with relative humidity kept under 50%. The facility is segmented into climate zones for different packaging formats, with certain areas reserved for international shipments that may require added humidity resistance or longer storage durations. Air handlers, industrial-grade dehumidifiers, and air filtration systems constantly regulate and cycle the air to maintain these parameters. Even the lighting systems are designed to minimize UV exposure, which could, over time, degrade packaging ink or food contact films. Once inside the warehouse, each pallet is scanned and logged into a warehouse management system. This system is fully integrated with the factory's enterprise resource planning software and allows operators to track not only where each pallet is stored, but exactly what production line, time, and ingredient lot was used to produce its contents. Each pallet label includes a unique serial number, barcode, and QR code that links to this full production history. This traceability is essential not just for internal logistics, but also for compliance with food safety regulations around the world, which require manufacturers to be able to track every product from raw ingredient to final point of sale. The WMS automatically arranges pallets by product type, batch date, and destination. Those scheduled for export may be routed to a separate staging zone where they will be checked for compliance with international packaging laws. Different markets may require translated labels, adjusted nutritional formats, or modified lot codes. Some export destinations also require additional tests, such as microbial swabs or accelerated shelf life sampling, to meet foreign government regulations. These are performed in an adjacent quality control annex, and only upon clearance are these pallets released to outbound logistics. Before any Oreo shipment leaves the facility, it undergoes a final visual inspection for physical damage to packaging, tamper seals, and box integrity. Any visible damage may indicate mishandling during internal transit or weak spots in pallet stability. Operators are trained to look for warped trays, compromised seals, or even small tears in the flow wrap film that could affect product freshness. Should any defect be discovered, that pallet is held for secondary inspection, and depending on severity, it may be repackaged or scrapped entirely. At this point, logistics coordinators use automated routing systems to schedule outbound shipments. These systems factor in geographic location, delivery deadlines, climate conditions, and truck availability. For example, shipments bound for warmer climates during the summer may be prioritized for insulated or refrigerated trucks to prevent the creme from softening. Long-haul shipments may be routed through distribution centers that offer cross-docking or climate-controlled storage to preserve product quality along the supply chain. The loading dock itself is operated with precision. Trucks arriving at the facility must be cleaned, inspected, and approved before any Oreo products are loaded. This includes visual inspection for pests, residue from prior shipments, and confirmation that the trailer temperature is within specification. Only after a truck passes these inspections does the facility open the dock door and begin the loading sequence. Robotic forklifts or human operators load the pallets according to pre-planned diagrams that ensure weight is evenly distributed and product is easily accessible at the destination. Each shipment is logged with time, driver ID, carrier information, route ID, and estimated delivery window. Once loaded, trucks are sealed with tamper-evident locks and dispatched with digital shipping documents, including delivery confirmations and scanned QR codes for receiving teams. The WMS updates the ERP system in real time, closing the inventory loop and marking the batch as shipped. This inventory and logistics traceability is crucial for meeting compliance with global food safety standards like the Global Food Safety Initiative, hazard analysis, and critical control points, and ISO 22000. Even after the Oreo product leaves the plant, the factory remains connected to its life cycle through digital feedback systems. Retailers and distributors have access to portal-based interfaces where they can report damages, delayed deliveries, or unexpected inventory issues. Returned products are scanned upon arrival at reverse logistics zones where factory staff investigate issues, analyze production records, and determine root causes. In cases where errors are found, such as premature staleness, flavor imbalance, or packaging failure, continuous improvement protocols are triggered to address the upstream causes. While these systems function to protect the product, they also feed into a broader factory goal: performance analytics and continuous optimization. The data from every shipment, temperature logs, shipping duration, breakage rates, seal integrity, and even consumer complaints is compiled into dashboards reviewed weekly by production leads, QA managers, and logistics coordinators. These dashboards enable the factory team to track KPIs like OTIF, defect per million rates, inventory turnover, spoilage reduction, and carbon footprint per pallet. Some Oreo plants are moving even further towards sustainability at this stage of production. Cardboard shipping boxes are made with recycled content and are themselves fully recyclable. Pallet wrap films are being downgauged or replaced with biodegradable alternatives. Facilities are experimenting with hybrid electric fleet partnerships or rail transport instead of trucks to reduce emissions. In select markets, even the plastic trays inside Oreo packs have been redesigned for recyclability, and clear labels now inform consumers on proper disposal. The journey begins with sourcing green coffee beans. Factories procure these beans in large quantities from coffee-growing regions such as Brazil, Colombia, Vietnam, and Ethiopia. Since instant coffee requires consistent flavor profiles, manufacturers often blend beans from various regions to create a balanced and standardized flavor. Upon arrival at the factory, the green coffee beans are subjected to rigorous quality control checks. Samples are tested for size, moisture content, and defects to ensure the beans meet the factory's standards for processing. Once approved, the beans are stored in massive silos made of food-grade stainless steel or aluminum to protect them from contamination, pests, and humidity. These silos are equipped with automated systems that precisely dispense beans onto the production line. The first major step in processing the beans is cleaning. Coffee beans, even after being cleaned at their origin, may still contain impurities such as dirt, stones, sticks, or metal fragments. In the factory, the cleaning process involves several stages. Vibrating screens sift the beans to remove large debris, while air classifiers blow away lighter materials, like husks or dust. Magnets are used to extract any metallic particles. Some factories also employ optical sorting machines, which use cameras and sensors to identify and remove defective beans or foreign objects. This thorough cleaning ensures that only high-quality beans proceed to the roasting stage. Roasting is a critical step in developing the rich, complex flavors of coffee. Factories use industrial coffee roasters, which can process thousands of pounds of beans per hour. The roasting process is controlled by highly advanced systems that allow operators to customize the roast profile for specific flavor outcomes. For instant coffee, medium to dark roasts are commonly used, as they bring out bold flavors that translate well into the final soluble product. Roasting temperatures typically range between 370 and 540 degrees Fahrenheit, depending on the desired flavor profile. During roasting, the beans undergo the Maillard reaction, a chemical process that creates the characteristic aromas and flavors of coffee. The roasting equipment includes temperature sensors and real-time monitoring systems to ensure uniform roasting across large batches. Once the roasting is complete, the beans are cooled rapidly to stop the roasting process and prevent overcooking. Factories use air cooling systems or water spray cooling, depending on the setup. Cooling is an important step, as improperly cooled beans can lose their flavor or become brittle. After cooling, the beans are sent to grinding machines. The grinding stage reduces the roasted coffee beans into smaller particles, which will be used for the brewing process. Factories use industrial grinders, such as roller mills or hammer mills, capable of producing a consistent grind size. The grind size is crucial because it affects the extraction process that follows. For instant coffee, a relatively coarse grind is typically used to optimize the brewing process in the factory. The ground coffee is then stored in intermediate holding bins, where it is kept fresh until it is ready to be brewed. Brewing is the next major step in instant coffee production, and it is carried out on an industrial scale. Massive brewing systems, similar to oversized percolators, are used to extract the soluble compounds from the ground coffee. These systems consist of large stainless steel extraction tanks or columns, which are designed to hold thousands of gallons of water and coffee grounds. Hot water is circulated through the coffee grounds at precise temperatures and pressures, mimicking the brewing process used at home, but on a much larger scale. Typically, water temperatures range between 190 and 205 degrees Fahrenheit, and the brewing time is carefully controlled to maximize flavor extraction while minimizing bitterness. The brewed coffee concentrate, a liquid containing the extracted soluble compounds, is then filtered to remove the spent coffee grounds. Factories use advanced filtration systems, such as centrifugal separators or fine mesh filters, to ensure that no solid particles remain in the liquid. The spent grounds are often dried and repurposed as fertilizer or biomass fuel, making use of every part of the raw material. At this stage, the coffee concentrate is a highly aromatic liquid, but it is still far from the final product. The challenge is to transform this liquid concentrate into a stable, dry, and soluble form. Factories use one of two main methods for this: spray drying or freeze drying. Spray drying is a fast and cost-effective method that is commonly used to produce instant coffee powder. The coffee concentrate is first preheated to reduce its moisture content. It is then pumped into a tall, spray drying chamber equipped with nozzles that disperse the liquid into fine droplets. At the same time, hot air, typically around 480 degrees Fahrenheit, is blown into the chamber. As the droplets fall through the chamber, the water in the coffee concentrate rapidly evaporates, leaving behind fine coffee powder. Spray drying is efficient and capable of processing large volumes, but the high temperatures can sometimes lead to a slight loss of flavor and aroma. Freeze drying, on the other hand, is a more delicate and sophisticated process that better preserves the natural flavors and aromas of coffee. The coffee concentrate is first frozen at extremely low temperatures, usually around 40 degrees Fahrenheit, to form solid slabs or granules. These frozen coffee pieces are then placed in a vacuum chamber. Inside the chamber, the frozen water in the coffee undergoes sublimation, a process where ice turns directly into vapor without passing through the liquid phase. This method requires precise control of temperature and pressure and takes longer than spray drying, but it produces high-quality granules of instant coffee that dissolve easily in water. After the drying process, the instant coffee is sifted and graded by particle size to ensure uniformity. Any oversized or undersized particles are removed, and the coffee is blended to create a consistent final product. Factories conduct rigorous quality control tests at this stage, including flavor analysis, solubility testing, and moisture content measurement. These tests ensure that the instant coffee meets the desired standards for flavor, aroma, and texture. Packaging is the final step in the production process, and it is designed to protect the coffee from moisture and preserve its freshness. The dried instant coffee is transported to high-speed filling machines, which dispense precise amounts of coffee into jars, tins, or pouches. Factories use nitrogen flushing systems to replace oxygen in the packaging, as oxygen can degrade the coffee over time. The jars are sealed with airtight lids, while pouches are heat-sealed to maintain freshness. After sealing, the packages move to labeling stations, where automated systems apply branding, ingredient lists, and expiration dates. Each package undergoes a final inspection using vision systems to ensure there are no defects in the seals or labels. Once approved, the packages are packed into cartons or cases using robotic packing systems and prepared for shipping. Pallets of instant coffee are stacked and wrapped for stability before being loaded onto trucks or containers for global distribution. Throughout the entire process, factories rely on advanced automation and engineering to ensure efficiency and consistency. Programmable logic controllers and supervisory control and data acquisition systems monitor and control every stage of production, from roasting and brewing to drying and packaging. Real-time data on temperature, pressure, humidity, and other parameters allows operators to make precise adjustments as needed, minimizing waste and ensuring high-quality output. Hygiene and food safety are also paramount in instant coffee production. Production areas are designed with food-grade stainless steel surfaces, seamless flooring, and clean room environments to prevent contamination. Positive air pressure systems are used to keep airborne particles out of critical areas, and employees are required to follow strict hygiene protocols, including wearing protective clothing and adhering to cleaning schedules. Factories are regularly inspected and certified to meet international food safety standards. Inside a tea factory, the transformation of fresh tea leaves into the familiar tea bags, loose leaf tea, or powdered varieties is a carefully orchestrated process. It is a seamless blend of tradition, precision engineering, and science. Every step of the way, from leaf intake to packaging, is designed to preserve the flavor, aroma, and quality that tea enthusiasts have come to expect. While the type of tea being produced, whether black, green, oolong, or white, dictates specific steps in the process, the overall journey is one of meticulous attention to detail, where both manual expertise and advanced machinery play vital roles. The process begins at the tea gardens, where leaves from the Camellia sinensis plant are plucked at peak quality. For most teas, workers handpick only the top 2 leaves and a bud from each branch, as these tender parts of the plant produce the best flavor and aroma. After harvesting, the leaves are transported to the factory as quickly as possible to prevent spoilage or fermentation during transit. Many tea factories are strategically located near plantations to minimize delays and ensure freshness. Upon arrival at the factory, the tea leaves are weighed and inspected for quality. Modern tea factories are equipped with automated intake systems that separate leaves from debris such as twigs or foreign matter. Vibrating conveyor belts or mechanical sieves are commonly used at this stage to remove unwanted materials. For higher grade teas, additional manual inspections may be carried out to ensure only the finest leaves proceed to the next step. The fresh leaves are then carefully spread out in thin layers on large trays or conveyor belts, marking the beginning of the first stage in tea processing. Withering. Withering is a critical step in tea production, as it reduces the moisture content of the fresh tea leaves and prepares them for the subsequent stages of processing. In the factory, withering is typically carried out in withering troughs, long, shallow trays equipped with a system of fans and controlled airflow. Fresh tea leaves are laid out on these trays, and air is circulated over them for several hours to slowly remove moisture. For black tea, withering may last anywhere from 12 to 18 hours, while green tea requires a shorter withering time, as it needs to retain more of its fresh, grassy flavor. Temperature and humidity are carefully controlled using automated climate systems to ensure consistent results. During this stage, the leaves become softer and more pliable, making them ready for rolling. The next stage is rolling, where the tea leaves are twisted and shaped to release their essential oils and initiate oxidation if required, as with black and oolong teas. Factories use large mechanical rolling machines equipped with heavy, grooved plates or rollers. These machines apply pressure to the leaves, breaking down their cell walls and releasing their natural juices. The released juices react with oxygen in the air, beginning the oxidation process that gives black tea its characteristic flavor and color. Rolling machines can be adjusted to produce different shapes and textures depending on the type of tea being made. For example, green teas may be rolled into tight pellets for varieties like gunpowder tea, while black teas are often left in long, wiry shapes. At this point, the production process diverges depending on the type of tea being manufactured. For black tea, oxidation is the next key step. Oxidation, often mistakenly referred to as fermentation, is a chemical process that darkens the tea leaves and develops the rich, robust flavors associated with black tea. In factories, oxidation typically takes place in large, temperature-controlled rooms, where rolled tea leaves are spread out on trays or conveyor belts. These rooms maintain a controlled environment with high humidity and a temperature of around 77 to 86 degrees Fahrenheit. The leaves are periodically monitored to ensure they achieve the desired level of oxidation, which can take anywhere from 30 minutes to several hours, depending on the tea. As the leaves oxidize, they turn from green to a reddish-brown color, releasing the aromatic compounds that define black tea. In contrast, for green tea production, oxidation is intentionally prevented. To preserve the vibrant green color and fresh vegetal flavor of the leaves, factories employ a process called fixation, also known as kill green. This step involves heating the leaves immediately after rolling to deactivate the enzymes that cause oxidation. Factories use either steam or dry heat for this purpose. For Japanese-style green teas, like sencha, the leaves are steamed in specialized machines, while Chinese-style green teas are often pan-fried in large heated woks or rotating drum roasters. Fixation requires precise temperature control, as overheating can burn the leaves and underheating can fail to stop oxidation completely. Once oxidation or fixation is complete, the next step is drying, which reduces the moisture content of the tea to make it shelf stable. Drying is typically carried out in large industrial dryers or ovens equipped with temperature controls and airflow systems. Conveyor belt dryers, in which the leaves are gradually moved through a heated chamber, are common in large-scale tea factories. The temperature during drying ranges from 194 to 248 degrees Fahrenheit, depending on the type of tea and the desired final moisture content, which is usually around 3 to 5%. This step is crucial for locking in the flavor and aroma of the tea while ensuring it will not spoil during storage. After drying, the tea leaves are sorted and graded. In the sorting process, leaves are separated by size, shape, and quality using a combination of vibrating sieves, air separators, and optical sorting machines. Whole leaves, broken leaves, and small particles are separated into different grades, which are used for various tea products. For instance, whole leaves are often reserved for premium loose-leaf teas, while smaller particles are used for tea bags. Some factories also employ advanced laser sorting machines that can detect and remove any remaining foreign objects or off-spec leaves. Blending is another key step in tea production, especially for brands that aim to create consistent flavor profiles. Many teas are blended by mixing leaves from different regions, harvests, or even types of tea. Blending is carried out in large rotating drums or mixing machines, where precise quantities of different teas are combined to achieve the desired flavor. For flavored teas, additional ingredients such as dried fruit pieces, herbs, or essential oils are added during this stage. For example, Earl Grey tea is made by blending black tea leaves with bergamot oil, while chai blends often include spices like cinnamon, cardamom, and cloves. Once the tea has been blended and sorted, it is ready for packaging. Packaging is a highly automated process in modern tea factories. For loose leaf tea, the leaves are weighed and sealed in airtight bags, tins, or foil-lined pouches to preserve freshness. For tea bags, the leaves are measured and packed into filter paper, which is then cut and sealed into individual tea bags using high-speed machines. Many factories also produce pyramid-shaped tea bags, which allow for larger leaves and better infusion. After filling, the tea bags are placed into cartons or boxes, which are sealed and labeled with branding, lot numbers, and expiration dates. Throughout the entire process, quality control plays a vital role in ensuring the tea meets rigorous standards. Factories employ trained tea tasters who sample the tea at various stages of production to assess its flavor, aroma, and appearance. Advanced laboratory equipment is also used to measure moisture content, microbial activity, and other parameters that affect the quality and safety of the final product. Additionally, factories must comply with food safety regulations and certifications, such as ISO 22000 or HACCP, to ensure their tea is safe for consumption. Cocoa powder, the cornerstone of countless recipes from rich chocolate cakes to creamy hot cocoa, is the product of a complex and fascinating manufacturing process that combines agricultural expertise with advanced industrial engineering. Behind every tin or packet of cocoa powder lies a detailed, multi-step operation where raw cacao beans are transformed into the fine, flavorful powder that has become a staple ingredient in kitchens around the world. This process begins on cacao farms and culminates in a factory where specialized equipment and precise techniques ensure the consistency, flavor, and quality of the finished product. Let's take an in-depth journey into how cocoa powder is made, exploring each stage of the process, from bean to powder. The story of cocoa powder begins with the cacao tree, which thrives in tropical regions near the equator, such as West Africa, Southeast Asia, and Central and South America. The cacao tree produces pods that contain cacao beans surrounded by a sweet, sticky pulp. These beans are the raw material for cocoa powder. Once harvested, the pods are split open to extract the beans, which are then immediately subjected to the first critical step in the process: fermentation. Fermentation is a natural and essential process that develops the flavor precursors in cacao beans. After being removed from the pods, the beans and their surrounding pulp are placed into shallow wooden boxes or large banana leaf-lined baskets, where they ferment over a period of 5 to 7 days. During this time, natural yeasts and bacteria break down the sugars in the pulp, generating heat and causing the temperature in the fermentation pile to rise significantly, often reaching over 120 degrees Fahrenheit. This heat triggers a series of chemical reactions within the beans, developing their characteristic chocolate flavor while reducing bitterness. The beans are turned periodically to ensure even fermentation and prevent spoilage. Once fermentation is complete, the beans are removed from the boxes or baskets and sent to the next stage: drying. Drying is critical for stabilizing the fermented beans and reducing their moisture content to a level suitable for storage and transport. Traditionally, cacao beans are dried under the sun, spread out in thin layers on large drying racks or patios, and turned regularly with wooden rakes to ensure even drying. In modern cocoa production, factories may use mechanical dryers when weather conditions are unsuitable for sun drying or to speed up the process. These machines blow heated air over the beans to achieve the target moisture content, which is usually around 6 to 7%. Proper drying is essential because any excess moisture could lead to mold growth during storage or shipping. Once dried, the beans are sorted, graded, and packed into jute bags or bulk containers, ready for shipment to processing facilities. Upon arriving at the cocoa processing factory, the dried cacao beans are carefully inspected for quality. Factories use advanced optical sorting machines equipped with cameras and lasers to identify and remove defective beans, such as those that are cracked, moldy, or undersized. Any remaining debris, like stones or twigs, is removed using vibrating screens and air separators. Once the beans are cleaned, they are stored in large silos made of food-grade stainless steel, which protects them from contamination while allowing for easy access as the beans move through the production line. The first step inside the factory is roasting, a critical stage that brings out the rich chocolatey aroma and flavor of the beans. Industrial roasters are designed to handle large volumes of cacao beans, roasting them at precise temperatures that can range from 250 to 300 degrees Fahrenheit. The exact temperature and duration of roasting depend on the type of cocoa powder being produced, as darker roasts develop more intense flavors, while lighter roasts preserve subtle fruity or floral notes. During roasting, the shells of the beans become brittle, and the internal nibs, which contain the cocoa solids and cocoa butter, begin to separate from the shell. Sensors and computer-controlled systems monitor the roasting process to ensure consistency across batches. Once roasting is complete, the beans are rapidly cooled using air or water to prevent overcooking. The next stage is winnowing, where the roasted beans are cracked open to separate the nibs from the outer shells. This process is carried out using winnowing machines, which use a combination of mechanical rollers and air currents to break the shells and blow them away. The result is a pile of clean, roasted nibs, which are the purest form of cacao and the raw material for all cocoa products. The nibs are then ground into a thick, viscous liquid known as cocoa liquor, despite containing no alcohol. The grinding process involves heavy-duty industrial grinders, such as roller mills or stone grinders, which crush the nibs into tiny particles. This process releases the natural cocoa butter within the nibs, creating a smooth liquid that flows easily. The particle size is reduced to less than 30 microns during this stage to ensure a silky texture. Cocoa liquor is the base ingredient for many chocolate products, but for cocoa powder production, the focus shifts to separating the two main components of the liquor, cocoa solids and cocoa butter. The separation of cocoa solids and cocoa butter is achieved through pressing. Cocoa liquor is fed into hydraulic or screw presses, which apply immense pressure, up to 6,000 pounds per square inch, to squeeze out the cocoa butter. This process leaves behind a solid cake of compressed cocoa solids. The extracted cocoa butter is collected and filtered for use in other products, such as chocolate bars, cosmetics, or pharmaceuticals. Meanwhile, the cocoa cake, which still contains a small amount of residual fat, becomes the foundation for cocoa powder. The cocoa cake is cooled and broken into smaller chunks before being fed into pulverizing machines, where it is ground into a fine powder. Factories use various types of grinding equipment, such as pin mills or ball mills, to achieve the desired particle size for cocoa powder. This step is critical for ensuring that the final product has a consistent texture and dissolves easily in liquids. The fineness of cocoa powder can vary depending on its intended use. For example, baking-grade cocoa powder is typically ground finer than drinking cocoa. At this point, the cocoa powder is almost ready, but one additional process may take place depending on the type of cocoa being produced: alkalization. Also known as Dutch processing. Alkalization involves treating the cocoa powder with an alkaline solution, such as potassium carbonate. This process neutralizes the natural acidity of the cocoa, darkens its color, and gives it a smoother, milder flavor. Alkalized cocoa powder is often used in baking and beverages, as its reduced acidity reacts differently with leavening agents like baking soda. Once the cocoa powder is fully processed, it undergoes rigorous quality control tests to ensure it meets the manufacturer's standards. Samples are tested for flavor, color, pH levels, fat content, and particle size. Factories use advanced laboratory equipment, such as spectrophotometers and viscometers, to measure these properties with precision. Any deviations from the desired specifications are identified and corrected before the product moves to the packaging stage. Packaging is the final step in the production process, and it plays a critical role in preserving the freshness and quality of the cocoa powder. The powder is first sifted to remove any clumps or oversized particles, ensuring a uniform texture. It is then transferred to automated filling machines, which dispense precise amounts of cocoa powder into containers such as tins, pouches, or bulk bags. For retail packaging, the containers are often flushed with nitrogen gas before sealing to remove oxygen and prevent spoilage. Labels are applied to the packages, including information such as the brand, product type, lot number, and expiration date. Once packaged, the cocoa powder undergoes a final round of inspections, where advanced vision systems check for defects such as improper sealing, misaligned labels, or damaged containers. The finished products are then packed into cartons or cases using robotic packaging systems. Palletizing robots stack the cartons neatly onto pallets, which are shrink-wrapped for stability and loaded onto trucks or shipping containers for distribution, creating